Hello, and welcome to another episode of the Book Club. Hello, Hossein. Thanks for tuning in. So today, we're going to be starting off by reading this paper that was in the further reading from the Computer Organization and Design. I wanted to read this paper here. Preliminary discussion of the logical design of an electronic computing instrument by Burks, Goldstine, and von Neumann. Welcome back, RISCY 5. I just started, so you didn't miss anything. And then the other thing is I remembered that we were doing the check yourself for the end of chapter 1. Reviewing my answers versus the answers in the book. And I forgot to finish that because when I was doing that, the YouTube... it's slightly out of order because I was doing that. I was doing the check yourself. And then since YouTube wasn't cooperating that day, I was going to do it in the next episode, and then I forgot and went on to the next chapter. So we're going to go back right now and do that. And then this says chapter 4 on here, but it's chapter 4 of something else. I don't know exactly what, but it's a research paper that was in the further reading at the end of the chapter. They recommended this paper, and apparently it's going to be referenced later on in the book. So I want to give it a read. And then also I'll point out before we get started here, if we go to the further reading, there were a few video recommendations in here. So this right here is the paper, that I want to read. And then right here we see Computer Pioneers and Pioneer Computers, which is a video series. And the Computer Museum actually has these available on YouTube, so I recommend checking those out. I watched them and they were very good. And then I ended up watching more like old computer videos from the related videos, but it's definitely worth checking out. So I just want to show you guys that quick. If we go search for Computer Pioneers, Pioneer Computers. So yeah, you see right here, the Computer History Museum has these up in full on YouTube, so you can watch those. And like I say, I recommend checking those out. It's just 2 parts. They're like an hour each. Very good stuff. And then the other one I checked out was the 5-part video series, which was also very good, and I'd recommend checking out. But you can't find all of them on YouTube. The Machine That Changed the World videotapes, this right here, I wasn't able to find all of them on YouTube. I found them on Pirate Bay, just in case you can't find a legal version. I don't know if you can even get this legally these days. It's from 1992. Like maybe you can find it on Netflix or something. I have no idea. I don't use Netflix, but yeah, if you can find a copy of this one way or another, it's a 5-part series, and it's definitely very interesting to check out too. I'd recommend it as well. But anyway, that's everything that I checked out from the further reading. And now we're just going to go through this. But before we do that, we need to continue with the check yourself. So let me see here. Yeah, exactly, Risky 5. So, GitHub. Oh, I've got it right here, don't I? Okay, so I want to review which ones we answered. So it looks like we were looking at chapter 1.13. Oh, that's the exercises, right? Okay, so let's jump to that video and just review where we left off here. So it's probably not going to let me click the thing, but I'll give it a try. Yeah, it just took me to the page here, so let's switch it to my personal account. Is it seriously going to do this again? What the heck, YouTube? Like, I mean, clearly things are able to load. YouTube is working, but the site breaks when I switch it to my personal account on here. So this time I was able to hit the YouTube home button. Let's switch it back to my Risky Business account. And let's try this in a different browser. All right, now take me to Risky Business. All right, I guess we should just do risky.tv. All right, here we go.
So we're going to skip these answers and we will look at them.
So I want to go just a little bit back from there.
No, can't click that button.
Yeah, today is a marathon Risky 5. I'm going to be doing, I'm thinking 2 book club episodes and 3 Risky Business episodes. Something like that. And I'll just be doing them back to back. Okay, just give me a moment here as I figure out. Yeah, we're watching. This is a video of me watching Risky Business, of an episode of me watching an episode of Risky Business. We're 3 layers deep at this point. Yeah, I didn't catch which one I was trying to watch there. Okay, I saw what we were looking at now. So this is book club day 4 that we want to go to now.
Your machine should never be able to.
All right, let's go to the check yourself.
So here we have.
All right, now let me open up the book here. Okay, so which one are we on?
Have a check yourself section. Suppose we know that an application that uses both personal mobile devices and the cloud is limited by network performance. For the following changes, state whether only the throughput improves, both response time and throughput improve, or neither improves. So these are lettered. A is an extra network channel is added between.
Okay, so we were looking at 1.6, page 33. So I'll reread the check yourself here. Suppose we know that an application that uses both personal mobile devices and the cloud is limited by network performance. For the following changes, state whether only the throughput improves, both response time and throughput improve, or neither improves. A is an extra network channel is added between the PMD and the cloud, increasing the total network throughput and reducing the delay to obtain network access, since there are now 2 channels. B is the networking software is improved, thereby reducing the network communication delay but not increasing throughput. C was more memory is added to the computer.
The PMD and the cloud, increasing the total network throughput and reducing the delay.
And let's see what my answers were here.
Since there are now 2 channels. B is the networking software is improved, thereby reducing the network communication delay, but not increasing throughput. C is more memory is added to the computer. So we're stating whether only the throughput improves, both response time and throughput, or neither. So B, they gave the answer, didn't they? In B, they said the networking software is improved, thereby reducing the network communication delay but not increasing the throughput. You just gave the answer in the description. It reduces the network communication delay. That is to say, it reduces the response time, but you didn't increase the throughput. You said it says right there, but not increasing throughput. I wonder if that was intentional or not.
So we said it seemed that they put the answers in the actual questions, and that B was it reduces the response time, and it says in here B is latency. So I suppose that's the same thing, isn't it? So they don't explicitly say it, but yeah, that would be the same thing, I think. Hello, Croeva. Thank you for tuning in.
C, where memory is set into the computer, that of course is not going to affect response time or throughput unless memory is actually a bottleneck.
So it looks like for C, I said.
A good example of that is when your computer starts swapping to disk, right? Where
For C, I said neither, but it could be a bottleneck if you were like swapping to disk, is what I said, and they just say neither in here.
your programs are using too much memory, then you're ramming out of your system, and it needs to actually swap out to disk. The operating system does that, unless you configure it to just crash programs and you're out of memory, right? But if you ever use swap, you probably experienced this, especially before as a student when you just were running hard drive. The experience of your system slowing down to a crawl and just being completely unusable. Everything's unresponsive, right? Because one process is using too much memory and everything starts swapping and it gets horribly slow because this IO is a big bottleneck, right? In that case, if you increase the amount of memory you have, you are actually reducing the
And then we want to see what A was. According to this, the answer for A is both. Let's see what I said.
if you increase the amount of RAM, you avoid less swapping, and then your system doesn't fall to holes, right? But in general, C would not reduce response time, and it would also not increase throughput, because we're talking about networking, not memory. We're changing unrelated components, basically. And for B, they already gave the answer, so the only one we actually need to answer now is A. An extra network channel is added between the Unity and the cloud. They give the answer in this one too. It says increasing the total network throughput and reducing the delay. So that wasn't much of a check yourself, was it? Okay, but then there's another one here. Number 2. Computer C's performance is 4 times.
Okay, so yeah, it was both, and it basically just says that in the. Croifo, where I was already looking at one where I attempted to review this before, so we've already gone 3 layers deep in the inception here. But in future chapters, what I'm gonna do is I'm gonna do the referencing the answers of the check yourself when I'm actually doing that check yourself, so I don't need to go back and review the video at the end of the chapter. But I didn't know the answers were in here, so I have to do it now.
Times as fast. Wait, let me reread this. Maybe I'm misunderstanding what they're asking. Suppose we know that an application uses both personal multiplexers and the cloud is limited by a performance. The performance changes stable. Yeah. So they just gave the answers briefly. I don't think that was intentional on the part of the author. I don't know. If I ever need
Okay, and then still page 33, there's another question. Okay, so its computer C's performance is 4 times as fast as the performance of computer B, which runs a given application in 28 seconds. How long will computer C take to run that application? And the answer here is 7 seconds. So let's see what I came up with.
So computer C is 4 times faster. So going on our metric here, assuming that there's no, assuming it's not perfect, it would be 4 times faster, right? So 28 divided by 4. But let's relate that back to our equations and see how you actually get that from the equations rather than just the obvious intuition of it. So we say the performance is, so we're defining n here. The performance of C is 4 times as fast. So n is 4 for C, vertical C over vertical B, right? So if we say T of Y over T of X, right? T of Y, computer B is running it in 28 seconds. So 28 T of X, and then this equals 10. And so we define n to be 4. So then we just need to do our algebra here. So
So in this episode, I was doing the algebra, but I guess I did it off screen because it was in the overlay, right? Because like I don't actually see the overlay on my computer; it's only on OBS. That's one thing I want to do with Milton is make it like draw a line where the overlay is going to be, so I know not to write in that portion. For the browser, what I do is I have a terminal window open on the right, so there's nothing in it. It's just used to like pad it, so that the browser is the uh, like all of it is on screen. But yeah, so I got 7 seconds. You can see that right here. Okay, and then there's going to be another check yourself on page 40. So let's jump to page 40. Okay, so it was a given application written in Java runs 15 seconds on a desktop processor. A new Java compiler is released that only requires 0.6 as many instructions. Unfortunately, it increases the CPI by 1.1. How fast can we expect the application to run using the new computer? And they gave us three choices, 8.2 seconds, 9.9 seconds, and 27.5 seconds. And let's see how I answered this one. So where is that check yourself in here? Right here.
And then there's a check yourself, and this is the end of the chapter here, or the end of the section. A given application for Java.
All right, and while I am reading that in the video, let me see what the answer is here. The answer is B. So it should be 9.9 seconds. Let's see what I answered here.
It says that the program that we're running takes 15 seconds from the first compiler. So equals 15.
This one I actually managed to write on the visible area for you guys.
How fast the application runs is looking for t equals b. And we know that the instructions for compiler B is to generate 0.6 times as many as compiler A. So I of B equals I of A times 0.6, but it increases the CPI by 1.1. So CPI of B equals 1.1 times CPI of A. And we're trying to find T of B. So let's just take a look through our equations here. First of all, we want to see how CPI is defined.
Let me see if I can skip forward a little bit.
Divided by the clock rate, right? Well, let's see here. Let's go a little bit higher here. We know the clock cycle is okay. That's over program times clock cycle seconds. So when we say seconds per program, I mean, isn't it 15 seconds per program? So we don't have that equals instructions of A. Okay. And then we're saying equals cycles A divided by the clock rate of A divided by 3. So, I mean, we've got three unknowns. We don't know the instructions, how many instructions it took for compiler A. 1.1. How fast? Because what's the law, the algebraic rule that like commutative or something? And so this is what I'm thinking. We have the T of A, which is 15. So we can actually check unless it has it somewhere here, like in the back.
Okay, so yeah, I got 9.9. You can see it right here.
Over 0.6 equals 27.5 seconds. So we would be going with answer B. That's the one that matches what we got.
So we got that correct. Let's go on to, I think there's one more check yourself here. page 51, there is one more check yourself. And it says the answer. I'll just read that off right away. There's an A and a B. A was computer A has the higher MIPS rating. B was computer B is faster. Page 51. Yeah, so they gave measurements for two programs, computer A and computer B. Computer A was 10 billion instructions, 4 gigahertz, 1.0 CPI. Computer B was 8 billion instructions, 4 gigahertz clock rate, and 1.1 CPI. And then they want to know which computer has the higher MIPS rating and which computer is faster. And like I said, computer A has the higher MIPS rating, but computer B is faster. And I'm pretty sure that's what I got as well, but let's double check. So that was section 1.10, so that's going to be in a different video. So 1.10. All right. That'll be this one here. Let's find the check yourself. Where is the check yourself? Oh, right here. So I said computer B is faster and computer A has the higher MIPS rating, which is what the correct answer was. All right. And like I say, in the future, I will streamline this. I'll do the comparison with the answers when I actually do the problems for the next chapters. All right, with that out of the way, today we are going to be reading this paper here from the further reading. Okay, so part 1, principal components of the machine. Inasmuch as the completed device will be a general-purpose computing machine, it should contain certain main organs relating to arithmetic, memory storage, control, and connection with the human operator. It is intended that the machine be fully automatic in character, that is, independent of the human operator, after the computation starts. A fuller discussion of the implications of this remark will be given in section 3 below. 1.2. It is evident that the machine must be capable of storing in some manner not only the digital information needed in a given computation, such as boundary values, tables of functions, such as the equation of state of a fluid, and also the intermediate results of the computation, which may be wanted for varying lengths of time, but also the instructions which govern the actual routine to be performed on the numerical data. In a special purpose machine, these instructions are an integral part of the device and constitute a part of its design structure. For an all-purpose machine, it must be possible to instruct the device to carry out any computation that can be formulated in numerical terms. Hence, there must be some organ capable of storing these program orders. I like how they were calling them organs. There must, moreover, be a unit which can understand these instructions and order their execution. Conceptually, we have discussed above two different forms of memory: storage of numbers and storage of orders. If, however, the orders of the machine are reduced to a numerical code, and if the machine can in some fashion distinguish a number from an order, the memory organ can be used to store both numbers and orders. The coding of orders into numeric form is discussed in 6.3 below. If the memory for orders is merely a storage organ, there must exist an organ which can automatically execute the orders stored in the memory. We shall call this organ the control. Inasmuch as the device is to be a computing machine, there must be an arithmetic organ in it which can perform certain of the elementary arithmetic operations. There will be, therefore, a unit capable of adding, subtracting, multiplying, and dividing. It will be seen in 6.6 below that it can also perform additional operations that occur quite frequently. The operations that the machine will view as elementary are clearly those which are wired into the machine. To illustrate, the operation of multiplication could be eliminated from the device as an elementary process if one were willing to view it as a properly ordered series of additions. Similar remarks apply to division. In general, the inner economy of the arithmetic unit is determined by a compromise between the desire for speed of operation. A non-elementary operation will generally take a long time to perform, since it is constituted of a series of orders given by the control, and the desire for simplicity or cheapness of the machine. Lastly, there must exist devices, the input and output organ, whereby the human operator and the machine can communicate with each other. This organ will be seen below in 4.5, where it is discussed to constitute a secondary form of automatic memory. First remarks of the memory. 2.1. It is clear that the size of the memory is a critical consideration in the design of a satisfactory general-purpose computing machine. We proceed to discuss what quantities the memory should store for various types of computations. In the solution of partial differential equations, the storage requirements are likely to be quite extensive. In general, one must remember not only the initial and boundary conditions and any arbitrary functions that enter the problem, but also an extensive number of intermediate results. A, for equations of parabolic or hyperbolic type in two independent variables, the integration process is essentially a double induction. To find the values of the dependent variables at time t plus delta t, one integrates with respect to x from one boundary to the other by utilizing the data at time t as if there were coefficients which contribute to defining the problem of this integration. Not only must the memory have sufficient room to store these intermediate data, but there must be provisions whereby these data can later be removed, that is, at the end of the t plus delta t cycle, and replaced by the corresponding data for the t plus 2 times delta t cycle. This process of removing data from the memory and of replacing them with new information must, of course, be done quite automatically under the direction of the control. For total differential equations, the memory requirements are clearly similar to, but smaller than, those discussed in A above. C. Problems that are solved by iterative procedures, such as systems of linear equations or elliptic partial differential equations, treated by relaxation techniques, may be expected to require quite extensive memory capacity. The memory requirements of such problems is apparently much greater than for those problems in A above, in which one needs only to store information corresponding to the instantaneous value of one variable, t, in A above, which, while now entire solutions covering all values of all variables must be stored. This apparent discrepancy in magnitudes can, however, be somewhat overcome by the use of techniques which permit the use of much coarser integration meshes, in this case, than in the cases under A. So really, historically here, they were motivated by some very specific mathematical problems, and I don't know if this was before or after Turing's work. I don't remember. But clearly they're kind of taking a look at certain classes of problems and arriving at what today we kind of take for granted as pretty standard concepts in the design of a computer. It is reasonable at this time to build a machine that can conveniently handle problems several orders of magnitude more complex than are now handled by existing machines, electronic or electromechanical. We consequently plan on a fully automatic electronic storage facility of about 4,000 numbers of 40 binary digits each. So back in this day, they weren't using power of 2 words yet. 40 binary digits. So that's a little weird. This corresponds to a precision of 2 to the negative 40 to, or I'm not sure what the tilde is specifying here. 0.9 times 10 to the negative 12th. I think that's maybe saying 2, so the range. The IBM 360. So then is this paper before the IBM 360? I mean, I watched the videos on the history of this stuff, but I don't remember the specifics. Oh, you're saying the 8-bit bytes came at that point. Yeah, so this was definitely before that. So they're saying of about 12 decimals of precision is what they're getting there. We believe that this memory capacity exceeds the capacities required for most problems that one deals with at present by a factor of about 10. The precision is also safely higher than what is required for the great majority of present-day problems. In addition, we propose that we have a subsidiary memory of much larger capacity, which is also fully automatic. On some median medium such as magnetic wire or tape. First, remarks on the control and code. It is easy to see by formal logical methods that there exist codes that are in abstracto adequate to control and cause the execution of any sequence of operations which are individually available in the machine and which are in their entirety conceivable by the problem planner. The really decisive considerations from the present point of view in selecting a code are more of a practical nature. Simplicity of the equipment demanded by the code, and the clarity of its application to the actual important problems, together with the speed of its handling of those problems. It would take us much too far afield to discuss these questions at all generally or from first principles. We will therefore restrict ourselves to analyzing only the type of code which we now envisage for our machine. So let me take a moment here. So this is Burks and Goldstine. I just want to review. So Burks worked on the ENIAC, and I want to know when this paper was done. I don't know if it's going to say in the Wikipedia page. So I think this was during the IAS stuff that this paper was written. Maybe before that? I see John von Neumann mentioned here. Maybe it was during the design of the EDVAC. I know it was mentioned when this was written, but I don't remember, and I kind of want to get the historical context here. And then we also need to see Goldstine. So they gave lectures, the Moore School lectures in 1946. So Goldstein met with von Neumann in 1944. So I think what we're reading here is a renamed, like a later renamed version of first draft of a report on the EDVAC, maybe? I'm not totally positive about that, but I know the history here is that von Neumann put his name on the paper and left their names out or whatever, and kind of stole the credit. And that's why we ended up with the term von Neumann architecture. So no, this is a different document then. Or maybe the paper that we're reading is a subset of it? I don't know. but like what we're talking about here is what we're talking about in the paper, so I'm not 100% sure where this paper falls in the history here, but it's definitely around the time of the EDVAC or the IAS stuff, somewhere in there when they met von Neumann. That's kind of the historical context of this paper. So anyway, let's keep reading here. So we were on first remarks of the controlling code. 3.2. There must certainly be instructions for performing the fundamental arithmetic operations. The specifications for these orders will not be completely given until the arithmetic unit is described in a little more detail. 3.3. It must be possible to transfer data from the memory to the arithmetic organ and back again. In transferring information from the arithmetic organ back into the memory, there are two types we must distinguish: transfers of numbers as such, and transfers of numbers which are parts of orders. The first case is quite obvious and needs no further explication. The second case is more subtle and serves to illustrate the generality and simplicity of the system. Consider, by way of illustration, the problem of interpolation in the system. Let us suppose that we have formulated the necessary instructions for performing an interpolation of order n in a sequence of data. The exact location in the memory of the n+1 quantities that bracket the desired functional value is, of course, a function of the argument. This argument probably is found as the result of a computation in the machine. We thus need an order which can substitute a number into a given order. In the case of interpolation, the location of the argument or the group of arguments that is nearest in our table to the desired value. By means of such an order, the results of a computation can be introduced into the instructions governing that or a different computation. This makes it possible for a sequence of instructions to be used with different sets of numbers located in different parts of the memory. To summarize, transfers into the memory will be of two sorts: total substitutions, whereby the quantity previously stored is cleared out and replaced by a new number, and partial substitutions, in which that part of an order containing a memory location number, we assume the various positions in the memory are enumerated serially by memory location numbers, is replaced by a new memory location number. It is clear that one must be able to get numbers from any part of the memory at any time. The treatment in the case of orders can, however, be more methodical, since one can at least partially arrange the control instructions in a linear sequence. Consequently, the control will be so constructed that it will normally proceed from place n in the memory to place n+1 for its next instruction. 3.5. The utility of an automatic computer lies in the possibility of using a given sequence of instructions repeatedly, the number of times it is iterated being either pre-assigned or dependent upon the results of the computation. When the iteration is completed, a different sequence of orders is to be followed, so we must, in most cases, give two parallel trains of orders preceded by an instruction as to which routine is to be followed. So here they're talking about the concept of flow control, like branches. This choice can be made to depend upon the sign of a number, 0 being reckoned as plus for machine purposes. Consequently, we introduce an order, the conditional transfer order, which will, depending on the sign of a given number, cause the proper one of two routines to be executed. Frequently, two parallel trains of orders terminate in a common routine. It is desirable, therefore, to order the control in either case to proceed to the beginning point of the common routine. This unconditional transfer can be achieved either by the artificial use of a conditional transfer or by the introduction of an explicit order for such a transfer. Finally, we need orders which will integrate the input-output devices with the machine. These are discussed briefly in 6.8. 3.7. We proceed now to a more detailed discussion of the machine. Inasmuch as our experience has shown that the moment one chooses a given component as the elementary memory unit, one has also more or less determined upon much of the balance of the machine. We start by a consideration of the memory organ. In attempting an exposition of a highly integrated device like a computing machine, we do not find it possible, however, to give an exhaustive discussion of each organ before completing its description. It is only in the final block diagrams that anything approaching a complete unit can be achieved. The time units to be used in what follows will be 1 microsecond and 1 millisecond, and they list what those are. The memory organ. 4.1. Ideally, one would desire an indefinitely large memory capacity such that any particular aggregate of 40 binary digits or word would be immediately available. That is, in a time which is somewhat or considerably shorter than the operation time of a fast electronic multiplier. This may be assumed to be practical at the level of about 100 microseconds. Hence, the availability time for a word in the memory should be 5 to 50 microseconds. It is equally desirable that words may be replaced with new words at about the same rate. It does not seem possible physically to achieve such a capacity. We are therefore forced to recognize the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding, but which is less quickly accessible. The most common form of storage, and I just gotta say, I'm a little surprised to see way back then they were already talking about memory hierarchies. So that's probably the most surprising thing I've read from this so far. I thought that was pretty interesting to see. Let's continue reading. The most common forms of storage in electrical circuits are the flip-flop or trigger circuit, the gas tube, and the electromechanical relay. And that's another thing. Zuse started out using the electromechanical relay in Germany and had the idea to use I think vacuum tubes was what they were going to after that, and it was because of like Hitler and the war that he kind of got set back, and nothing really became of it. Whereas in the United States, progress continued, and the U.S. was able to achieve that first. The first fully electronic computer, that is, using vacuum tubes. I believe that's the correct history there, if I'm remembering properly. To achieve a memory of n words would, of course, require about 40 n such elements, exclusive of the switching elements. We saw earlier in 2.2 that a fast memory of several thousand words is not at all unreasonable for an all-purpose instrument. Hence, about 10 to the 5th flip-flops or analogous elements would be required. This would, of course, be entirely impractical. We must therefore seek out some more fundamental method of storing electrical information that has been suggested above. One criterion for such a storage medium is that the individual storage organs, which accommodate only one binary digit each, should not be macroscopic components, but rather microscopic elements of some suitable organ. They would then, of course, not be identified and switched to by the usual macroscopic wire connections, but by some functional procedure in manipulating that organ. One device which displays this property to a marked degree is the Iconoscope tube. I've never heard of an Iconoscope tube. What is an Iconoscope tube? The first practical video camera tube. Interesting. Used in early television cameras. It produced a stronger signal than early mechanical designs and could be used under any well-lit conditions. So it looks like this was invented, or at least patented, around 1923. Interesting. I'm not going to dive too deep into that, but that was interesting to see. In its conventional form, it possesses a linear resolution of about 1 part in 500. This would correspond to a two-dimensional memory capacity of 500 by 500, which is 2.5 times 10 to the 5th. One is accordingly led to consider the possibility of storing electrical charges on a dielectric plate inside a cathode ray tube. Effectively, such a tube is nothing more than a myriad of electrical capacitors which can be connected into the circuit by means of an electron beam. Actually, the above mentioned high resolution and concomitant, I'm not familiar with that word, concomitant, naturally accompanying or associated, or a phenomenon that naturally accompanies or follows something. Actually, the above-mentioned high resolution and concomitant, and I didn't bother looking at the pronunciation there, so I might be pronouncing it wrong, but memory capacity are only realistic under the conditions of television image storage, which are much less exigent in respect to the reliability of individual markings than what one can accept in the storage for a computer. In this latter case, resolutions of 1 part in 20 to 100, that is, memory capacities of 400 to 10,000, would seem to be more reasonable in terms of equipment built essentially along familiar lines. At the present time, the Princeton laboratories of the Radio Corporation of America are engaged in the development of a storage tube, the Selectron, of the type we have mentioned above. So, I mean, if we're talking about Princeton laboratories, this must have been around the time of the IAS then, right? Because that was Princeton. And we see the EDVAC mentioned down here. So we're kind of gleaming where this fits in history just from that. So the Selectron of the type we have mentioned above, this tube is also planned to have a non-amplitude sensitive switching system whereby the electron beam can be directed to a given spot on the plate within a quite small fraction of a millisecond. Inasmuch as the storage tube is the key component of the machine envisaged in this report, we are extremely fortunate in having secured the cooperation of the RCA group in this, as well as in various other developments. An alternative form of rapid memory organ is the acoustic feedback delay line, described in various reports of the EDVAC. So yeah, it is after the EDVAC that this is written. This is an electronic computing machine being developed for they're saying, okay, it's being developed. So it was during the development, I guess, of the EDVAC. This is an electronic computing machine being developed for the Ordnance Department of the U.S. Army by the University of Pennsylvania Moore School of Electrical Engineering. Inasmuch as that device has been so clearly reported in those papers, we give no further discussion. There are still other physical and chemical properties of matter in the presence of electrons or photons that might be considered, but since none is yet beyond the early discussion stage, we shall not make further mention of them. And progress certainly did speed right along in that area. We shall accordingly assume throughout the balance of the report that the selectron is the modus for storage of words at electronic speeds. As now planned, this tube will have a capacity of 2 to the 12th, or 4096, which they say is approximately 4,000 binary digits. To achieve a total electronic storage of about 4,000 words, we propose to use 40 selectrons, thereby achieving a memory of 2 to the 12th words of 40 binary digits each. 4.3. There are two possible means for storing a particular word in the selectron memory, or in fact in either a delay line memory or in a storage tube with amplitude-sensitive deflection. One method is to store the entire word in a given tube and then to get the word out by picking out its respective digits in a serial fashion. The other method is to store in corresponding places in each of the 40 tubes one digit of the word. To get a word from the memory in this scheme requires then one switching mechanism to which all 40 tubes are connected in parallel. Such a switching scheme seems to us to be simpler than the technique needed in the serial system and is of course 40 times faster. We accordingly adopt the parallel procedure and thus are led to consider a so-called parallel machine as contrasted with the serial principles being considered for the EDVAC. In the EDVAC, the peculiar characteristics of the acoustic delay line, as well as various other considerations, seem to justify a serial procedure. For more details, see the reports referred to in 4.1. The essential difference between these two systems lies in the method of performing an addition. In a parallel machine, all corresponding pairs of digits are added simultaneously, whereas in a serial one, these pairs are added serially in time. To summarize, we assume that the fast electronic memory consists of 40 selectrons, which are switched in parallel by a common switching arrangement. The inputs of the switch are controlled by the control. Inasmuch as a great many highly important classes of problems require a far greater total memory than 2 to the 12th words, we now consider the next stage in our storage hierarchy. Although the solution of partial differential equations frequently involves the manipulation of many thousands of words, these data are generally required only in blocks which are well within the 2 to the 12th capacity of the electronic memory. Our second form of storage must therefore be a medium which feeds these blocks of words to the electronic memory. It should be controlled by the control of the computer and is thus an integral part of the system, not requiring human intervention. There are evidently two distinct problems raised above. One can choose a given medium for storage, such as teletype tapes, magnetic wire, or tapes, movie film, or similar media. There still remains the problem of automatic integration of the storage medium with the machine. This integration is achieved logically by introducing appropriate orders into the code which can instruct the machine to read or write on the medium, or to move it by a given amount, or to a place with given characteristics. We discussed this question a little more fully in 6.8. Let us return now to the question of what properties the secondary storage medium should have. It clearly should be able to store information for periods of time long enough so that only a few percent of the total computing time is spent in re-registering information that is fading off. It is certainly desirable, although not imperative, that information can be erased and replaced by new data. The medium should be such that it can be controlled, that is, moved forward and backward automatically. This consideration makes certain media, such as punch cards, undesirable. While cards can, of course, be printed or read by appropriate orders from some machine, they are not well adapted to problems in which the output data are fed directly back into the machine and are required in a sequence which is non-monotone with respect to the order of the cards. The medium should be capable of remembering very large numbers of data at a much smaller price than electronic devices. It must be fast enough so that even when it has to be used frequently in a problem, a large percentage of the total solution time is not spent in getting data into and out of this medium and achieving the desired positioning on it. If this condition is not reasonably well met, the advantages of the high electronic speeds of the machine will be largely lost. Both light or electron-sensitive film and magnetic wires or tapes whose motions are controlled by servo mechanisms integrated with the control would seem to fulfill our needs reasonably well. We have tentatively decided to use magnetic wires since we have achieved reliable performance with them at pulse rates of the order of 25,000 per second and beyond. 4.6. Lastly, our memory hierarchy requires a vast quantity of dead storage, that is, storage not integrated with the machine. This storage requirement may be satisfied by a library of wires that can be introduced into the machine when desired and at that time become automatically controlled. Thus, our dead storage is really nothing but an extension of our secondary storage medium. It differs from the latter only in its availability to the machine. 4.7. We impose one additional requirement on our secondary memory. It must be possible for a human to put words on the one wire or other substance, or for a human to put words onto the wire or other substance used and to read the words put on by the machine. In this manner, the human can control the machine's functions. It is now clear that the secondary storage medium is really nothing other than a part of our input-output system. See 6.8.4 for a description of a mechanism for achieving this. 4.8. There is another highly important part of the input-output which we merely mention at this time, namely some mechanism for viewing graphically the results of a given computation. This can, of course, be achieved by a selectron-like tube, which causes its screen to fluoresce when data are put on it by an electron beam. 4.9. For definiteness, in the subsequent discussions, we assume that associated with the output of each electron is a flip-flop. This assemblage of 40 flip-flops we term the selectron register. Section 5, the arithmetic organ. In this section, we discuss the features we now consider desirable for the arithmetic part of our machine. We give our tentative conclusions as to which of the arithmetic operations should be built into the machine and which should be programmed. Finally, a schematic of the arithmetic unit is described. 5.2. In a discussion of the arithmetical organs of a computing machine, one is naturally led to a consideration of the number system to be adopted. In spite of the long-standing tradition of building digital machines in the decimal system, we feel strongly in favor of the binary system for a device. Okay, so they really kind of were one of the first pioneers of using the binary system as opposed to trying to use decimal within a digital setting. Our fundamental unit of memory is naturally adapted to the binary system, since we do not attempt to measure gradations of charge at a particular point in this electron, but are content to distinguish two states. The flip-flop, again, is a truly binary device. On magnetic wires or tapes, and in acoustic delay line memories, one is also content to recognize the presence or absence of a pulse, or if a carrier frequency is used, of a pulse train, or of the sign of a pulse. We will not discuss here the ternary possibilities of a positive or negative or null pulse system and their relationship to questions of reliability and checking, nor the very interesting possibilities of carrier frequency modulation. Hence, if one contemplates using a decimal system with either the Iconoscope or a delay line memory, one is forced into a binary coding of the decimal system, each decimal digit being represented by at least a tetrad of binary digits. Thus, an accuracy of 10 decimal digits requires at least 40 binary digits. In a true binary representation of numbers, however, about 33 digits suffice to achieve a precision of 10 to the 10th. The use of the binary system is therefore somewhat more economical of equipment than is the decimal. The main virtue of the binary system, as against the decimal, is, however, the greater simplicity and speed with which the elementary operations can be performed. To illustrate, consider multiplication by repeated addition. In binary multiplication of the product of a particular digit of the multiplier by the multiplicand is either the multiplicand or null according to the multiplier digit, or according as the multiplier digit is 1 or 0. In the decimal system, however, this product has 10 possible values between null and 9 times the multiplicand, inclusive. Of course, a decimal number has only log 10 2 to 0.3 times inclusive. Of course, I read back onto the same line. Times as many digits as a binary number of the same accuracy. But even so, multiplication in the decimal system is considerably longer than in the binary system. One can accelerate decimal multiplication by complicating the circuits, but this in fact is irrelevant to the point just made, since binary multiplication can likewise be accelerated by adding to the equipment. Similar remarks may be made about the other operations. An additional point that deserves emphasis is this: an important part of the machine is not arithmetical, but logical in nature. Now, logics, being a yes-no system, is fundamentally binary. Therefore, a binary arrangement of the arithmetical organs contributes very significantly towards producing a more homogeneous machine, which can be better integrated and is more efficient. The one disadvantage of the binary system, from the human point of view, is the conversion problem. Since, however, it is completely known how to convert numbers from one base to another, and since the conversion can be affected solely by the use of the usual arithmetic processes, there is no reason why the computer itself cannot carry out this conversion. It might be argued that this is a time-consuming operation. This, however, is not the case. They give some references in 9.6 and 9.7 of Part 2. Part 2 is a report issued under the title Planning and Coding of Problems for an Electronic Computing Instrument. Indeed, a general-purpose computer used as a scientific research tool is called upon to do a very great number of multiplications upon a relatively small amount of input data, and hence the time consumed in the decimal to binary conversion is only a trivial percentage of the total computing time. A similar remark is applicable to the output data. In the preceding discussion, we have tactfully assumed that the desirability of introducing and withdrawing data in the decimal system. We feel, however, that the base 10 may not even be a permanent feature in a scientific instrument, and consequently will probably attempt to train ourselves to use numbers base 2 or 8 or 16. The reason for the bases 8 or 16 is this: since 8 and 16 are powers of 2, the conversion to binary is trivial. Since both are about the size of 10, they violate many of our habits less badly than base 2. And of course, today we do use things like octal and hex. Several of the digital computers being built or planned in this country and England are to continue a so-called floating decimal point. This is a mechanism for expressing each word as a characteristic and mantissa. An example being 123.45 would be carried in the machine as 0.1234503, where the 3 is the exponent of 10 associated with a number. There appear to be two major purposes in a floating decimal point system, both of which arise from the fact that the numbers of digits in a word is a constant fixed by design consideration for each particular machine. The first of these purposes is to retain in a sum or product as many significant digits as possible, and the second of these is to free the human operator from the burden of estimating and inserting into a problem scale factors, multiplicative constants which serve to keep the numbers within the limits of the machine. There is, of course, no denying the fact that human time is consumed in arranging for the introduction of suitable scale factors. We only argue that the time so consumed is a very small percentage of the total time we spend in preparing an interesting problem for our machine. The first advantage of the floating point is, we feel, somewhat illusory. In order to have such a floating point, one must waste memory capacity, which could otherwise be used for carrying more digits per word. It would therefore seem to us not at all clear whether the modest advantages of a floating binary point offset, the loss of memory capacity, and the increased complexity of the arithmetic and control circuits. And of course, these days floating point is common. There are certainly some problems within the scope of our device which really require more than 10 to the negative 40 precision. To handle such problems, we wish to plan in terms of words whose lengths are some fixed integral multiple of 40, and program the machine in such a manner as to give the corresponding aggregates of 40-digit words the proper treatment. We must then consider an addition or multiplication as a complex operation programmed from a number of primitive additions or multiplications. There would seem to be considerable extra difficulties in the way of such a procedure in an instrument with a floating binary point. The reader may remark upon our alternate spells of radicalism and conservatism in deciding upon various possible features for our mechanism. We hope, however, that he will agree, on closer inspection, that we are guided by a consistent and sound principle in judging the merits of any idea. We wish to incorporate into the machine, in the form of circuits, only such logical concepts as are either necessary to have a complete system or highly convenient because of the frequency with which they occur and the influence they exert in the relevant mathematical situations. 5.4. On the basis of this criterion, we definitely wish to build into the machine circuits which will enable it to form the binary sum of two 40-digit numbers. We make this decision not because addition is a logically basic notion, but rather because it would slow the mechanism as well as the operator down enormously if each addition were programmed out of the more simple operations of and, or, and not. The same is true for the subtraction. Similarly, we reject the desire to form products by programming them out of additions. The detailed motivation being very much the same as in the case of addition and subtraction. The cases for division and square rooting are much less clear. It is well known that the reciprocal of a number a can be formed to any desired accuracy by iterative schemes. One such scheme consists of improving an estimate x by forming x prime equals 2x minus ax squared. Thus the new error 1 minus ax prime is 1 minus ax squared, which is the square of the error in the preceding estimate. We notice that in the formation of x prime, there are two bona fide multiplications. We do not consider multiplication by 2 as a true product, since we will have a facility for shifting right or left in 1 or 2 pulse times. If then we somehow could guess 1 over a to a precision of 2 to the negative fifth, 6 multiplications, 3 iterations would suffice to give a final result good to 2 to the negative 40. Accordingly, a small table of 2 to the 4 entries could be used to get the initial estimate of 1 over a. In this way, a reciprocal 1 over a could be formed in 6 multiplication times, and hence a quotient b over a in 7 multiplication times. Accordingly, we see that the question of building a divider is really a function of how fast it can be made to operate compared to the iterative method sketched above. In order to justify its existence, a divider must perform a division in a good deal less than 7 multiplication times. We have, however, conceived a divider that is much faster than these 7 multiplication times, and therefore feel justified in building it, especially since the amount of equipment needed above the requirements of the multiplier is not important. It is, of course, also possible to handle square roots by iterative techniques. In fact, if x is our estimate of a to 1/2, then x prime equals 1/2 x plus a over x is a better estimate. we see that this scheme involves one division per iteration. As will be seen below in our more detailed examination of the arithmetic argon, we do not include a square rooter in our plans because such a device would involve more equipment than we feel is desirable in a first model. The first part of our arithmetic argon requires little discussion at this point. It would be a parallel storage argon, which can receive a number and add it to the one already in it, which is also able to clear its contents and which can transmit what it contains. We will call such an argon an accumulator. It is quite conventional in principle in past and present computing machines of the most varied types, examples being desk multipliers, standard IBM computers, more modern relay machines, and ENIAC. There are, of course, numerous ways to build such a binary accumulator. We distinguish two broad types of such devices: static and dynamic or pulse type accumulators. These will be discussed in 5.11, but it is first necessary to make a few remarks concerning the arithmetic of binary addition. In a parallel accumulator, the first step in an addition is to add each digit to the addend to the corresponding digit of the augend. The second step is to perform the carries, and this must be done in sequence since a carry may produce a carry. In the worst case, 39 carries will occur. Clearly, it is inefficient to allow 39 times as much time for the second step, performing the carries, as for the first step, adding the digits. Hence, either the carries must be accelerated, or use must be made of the average number of carries, or both. 5.6. We shall show that for a sum of binary words, each of length n, the length of the largest carry sequence is on the average not in excess of 2 log n. Let PNV designate the probability that a carry sequence is of length v or greater in the sum of two binary words of length n. Then clearly PNV minus PNV plus 1 is the probability of the largest carry sequence is of length exactly v, and the weighted average an equals sigma v equals 0 to n, v pn v minus p n v plus 1 is the average length of such a carry. Note that sigma v from 0 to n pnv minus pnv plus 1 equals 1, since pnv equals 0 if v is greater than n. From these, it is easily inferred that an equals sigma v equals 1 to n pnv. We now proceed to show that pnv is less than or equal to min 1 n minus v plus 1 over 2 to v plus 1. Observe first that pnv equals pn minus 1 v plus 1 minus pn minus v over 2v plus 1, or 2 to the power of v plus 1, if v is less than or equal to n. So that was quite a mouthful of equations there. I'm not going to take time to think about those, but we're going to keep reading here. Indeed, PNV is the probability that the sum of two n-digit number contains a two numbers. Later, Risky 5. Thank you for tuning in. Let's see here. The probability that the sum of two n-digit numbers contains a carry sequence of length greater than or equal to v. This probability obtains by adding the probabilities of two mutually exclusive alternatives. First, either the n-1 first digits of the two numbers by themselves contain a carry sequence of length greater than or equal to v. This is the probability p n-1 v. Second, the n-1 first digits of the two numbers by themselves do not contain a carry sequence of length greater than or equal to v. In this case, any carry sequence of length greater than or equal to v and the total numbers of length n must end with the last digits of the total sequence. Hence, these must form the combination 1, 1. The next v minus 1 digits must propagate the carry. Hence, each of these must form the combination 1, 0 or 0, 1. The combinations 1, 1 and 0, 0 do not propagate a carry. Oh, so I know what they're talking about here. I had a sleepless night some time ago. Let me open my work Milton canvas. I put it here. I was thinking about carry lookahead adders because I've never done a carry lookahead adder. I did the naive full adder in Minecraft way back in the day, which is why I was familiar with it. But I never did a carry lookahead adder. I knew that that was a thing, but I never did one myself. So I had a sleepless night a while back where I was thinking about carry lookahead adders and how that would work, how you would do a carry lookahead without like looking it up. I was just trying to work through the logic of how you could do a carry lookahead. And so I was doing various tables just to see the patterns. And I noticed you get runs of ones that propagate through, and the points where they don't propagate are, as they say, the 1-1s and the 0-0s. Like if you write it out and do the logic tables like you see I did here, you see like I circled them right here in this particular example, and I was showing, like, as I was working through it, and here I'm showing again the ones, and I didn't do the 0 here because I was thinking about other things. I don't remember the exact details of what I was working through here, but yeah, I've done this where I kind of started to work through the logic. I didn't get all the way to having an actual carry lookahead adder circuit, but I was thinking about the logic of it just because, like I say, I had a sleepless night and it was on my mind. And that's what they're working through here, basically. But they took a more mathematical approach of these equations, whereas I was just, looking at the logic of it, of doing it on paper, the ones and zeros, and seeing the patterns. So that's interesting to me, just from my own experience, seeing them, doing this stuff, and then it's like, oh, hey, I recognize that. That's kind of cool to see. The probabilities of the combination 1-1 is 1/4 that one of the alternative combinations 1-0 or 0-1 is 1/2. The total probabilities of the sequence is therefore 1/4, 1/2 v minus 1 equals 1/2 v plus 1. The remaining n minus v digits must not contain a carry sequence of length greater than or equal to v. This has the probability 1 minus pn or pn minus v, v. Thus the probability of the second case is 1 minus pn minus v, v over 2 to the v plus 1. Combining these two cases, the desired relation pn v equals p n minus 1 v plus 1 minus pn minus v, v over 2 to the v plus 1 obtains the observation that pn v equals 0 if v greater than n is trivial. We see with the help of the formulas proved above that pnv minus pn minus 1v is always less than or equal to 1/2 v plus 1, and hence that the sum sigma I equals v to n for pi v minus pi minus 1v equals pnv is not in excess of n minus v plus 1 over 2 to the v plus 1. Since there are n minus v plus 1 terms in the sum, since moreover each pnv is a probability, it is not greater than 1. Hence we have pnv is less than or equal to min 1 n minus v plus 1 over 2 to the n plus 1. Finally, we turn to the question of getting an upper bound on an equals sigma v to n for 1 pnv. Choose k so that 2 to the k is less than or equal to n is less than or equal to 2 to the k plus 1. Then a to the n equals sigma of v equals 1 to k minus 1 pnv plus sigma of v equals k to n of pnv is less than or equal to sigma of v equals 1 to k minus 1 plus sigma v equals k to the n over 2 to the v plus 1 equals k minus 1 plus n over 2 to the k. So that was pretty ridiculous to read, but okay. Hopefully that's the end of the crazy equations. It looks like it's not, though. Now where was I? I lost my place. Okay, right here. The last expression is clearly linear in n in the interval 2 to the k is less than or equal to n is less than or equal to 2 to the k plus 1, and it is equal to k for n equals 2 to the k and equals to k plus 1 for n equals 2 to the k plus 1. That is, it is equal to 2 log n at both ends of this interval. Since the function 2 log n is everywhere concave from below, it follows that our expression is less than or equal to 2 log n throughout this interval. Thus, an is less than or equal to 2 log n. This holds for all k, that is for all n, and it is the inequality which we wanted to prove. Man, they really dive deep into studying the problem of carries here. So I wonder if this is some of the first work on doing like carry lookahead. It seems like that might be the case. For our case, n equals 40, we have an is less than or equal to log 2 40 to 5.3. That is an average length of about 5 for the longest carry sequence. The actual value of A40 is 4.62. Okay, 5.7. Having discussed the addition, we can now go on to the subtraction. It is convenient to discuss at this point our treatment of negative numbers, and in order to do that right, it is desirable to make some observations about the treatment of numbers in general. So I wonder if they use 2's complement here. I'm guessing they do, but we will find out. It might be before that was a common thing. I don't know. Our numbers are 40-digit aggregates, the leftmost digit being the sign digit, and the other digits genuine binary digits, with positional values 2 to the minus 1, 2 to the minus 2nd, all the way to 2 to the minus 39, going from left to right. Our accumulator will, however, treat the sign digit 2 as a binary digit with a positional value 2 to the 0, at least when it functions as an adder. For numbers between 0 and 1, this is clearly all right. The leftmost digit will then be 0, and if 0 at this place is taken to represent a plus sign, then the number is correctly expressed with its sign in 39 binary digits. And again, I went over this stuff on Risky Business when we looked at the implementation of a full adder and we're studying 2's complement. So this is familiar to me, and should be to you as well if you watch Risky Business. Let us now consider what are more unrestricted 40 binary digit numbers. The accumulator will add them with the digit adding and the carrying mechanisms functioning normally and identically in all 40 positions. There is one reservation, however. If a carry originates in the leftmost position, then it has nowhere to go from there. There being no further positions to the left, and is lost. This means, of course, that the addend and the augend, both numbers between 0 and 2, produce a sum exceeding 2, and the accumulator, being unable to express a digit with a positional value to the 2 to the 1, which would now be necessary, omitted 2. That is the sum we formed correctly, accepting a possible error 2. If several such additions are performed in succession, then the ultimate error may be any integer multiple of 2. That is, the accumulator is an adder which allows errors that are integer multiples of 2. It is an adder modulo 2. It should be noted that our convention of placing the binary point immediately to the right of the leftmost digit has nothing to do with the structure of the adder. In order to make this point clearer, we proceed to discuss the possibilities of positioning the binary point in somewhat more detail. We begin by enumerating the 40 digits of our numbers, words, from left to right. In doing this, we use an index h equals 1 to 40. Now we must have placed the binary digit, or the binary point, just as well between digits I and I plus 1. I equals 0 to 40. Note that I equals 0.0 corresponds to the position at the extreme left. There is no digit h equals I equals 0. I equals 40 corresponds to the position at the extreme right. There is no position h equals I plus 1 equals 41. And I equals 1 corresponds to our above choice. Whatever our choice of I, it does not affect the correctness of the accumulator's addition. This is equally true for subtraction. See below, but not for multiplication and division, section 5.8. Indeed, we have merely multiplied all numbers by 2 to the I minus 1, as against our previous convention, and such a change of scale has no effect on addition and subtraction. However, now the accumulator is an adder, which allows errors that are integer multiples of 2 to the I. It is an adder modulo 2 to the I. We mention this because it is occasionally convenient to think in terms of a convention which places the binary points at the right end of the digital aggregate. Then I equals 40, our numbers are integers, and the accumulator is an adder modulo 2 to the 40. And that's how we commonly use an adder today. If we're doing decimals, we're probably using a floating point unit instead, right? We must emphasize, however, that all of this, that is, all attributions of values to I, are purely convention. That is, it is solely the mathematician's interpretation of the functioning of the machine and not a physical feature of the machine. This convention will necessitate measures that have to be made effective by actual physical features of the machine. That is, the convention will become a physical and engineering reality only when we come to the organs of multiplication. We will use the convention I equals 1, and that is our numbers lie in 0 and 2, and the accumulator adds modulo 2. This being so, these numbers between 0 and 2 must be used to represent all numbers modulo 2. Any real number x agrees modulo 2 with one and only number x bar between 0 and 2, or to be quite precise, 0 is less than or equal to x bar less than 2. Since our addition functions modulo 2, we see that the accumulator may be used to represent and to add numbers modulo 2. This determines the representation of negative numbers. Okay, so that's kind of interesting that they approached their choice of representation of negative numbers based on this kind of like fixed point use of an adder. If x is less than 0, then we have to find the unique integer multiple of 2. 2s. S equals 1, 2, and so on, such that 0 is less than or equal to x bar is less than 2 for x bar equals x plus 2s, i.e. minus 2s is less than or equal to x is less than 2, 1 minus s, and represent x by the digitalization of x bar. In this way, however, the sign digit character of the leftmost digit is lost. It can be 0 or 1 for both x is greater than or equal to 0 and x is less than 0. Hence, 0 in the leftmost position can no longer be associated with the plus sign of x. This may seem a bad deficiency of the system, but it is easy to remedy, at least to an extent which suffices for our purposes. This is done as follows. So then they're using a weird representation of... So, I mean, that's not 2's complements. If 0 can be... If the sign bit isn't the high-end bit. So let's continue reading here. We usually work with numbers x between -1 and 1, or to be quite precise, -1 is less than or equal to x is less than 1. Now the x bar with 0 is less than or equal to x bar less than 2, which differs from x by an integer multiple of 2, behaves as follows. If x is greater than or equal to 0, then 0 is less than or equal to x is less than 1. Hence, x bar equals x, and so 0 is less than or equal to x bar is less than 1. The leftmost digit of x bar is 0. If x is less than 0, then -1 is less than or equal to x is less than 0. Hence, x bar equals x plus 2, and so 1 less than or equal to x bar less than 2. The leftmost digit of x bar is 1. Thus, the leftmost digit of x bar is now a precise equivalent of the sign of x. 0 corresponds to plus and 1 to minus. So I don't follow all the logic they just did there. I don't understand how they're representing negative numbers. This is presented in a little too archaic of methodology here for me to really follow, I guess. Summing up, the accumulator may be taken to represent all real numbers modulo 2, and it adds them modulo 2 if x lies between -1 and 1. Precisely -1 is less than or equal to x is less than 1, as it will in almost all of our uses of the machine. Then the leftmost digit represents the sign, 0 is plus and 1 is negative. Consider now a negative number x with -1 is less than or equal to x is less than 0. put x equals negative y, 0 is less than y is less than or equal to 1. Then we digitalize x by representing it as x plus 2 equals 2 minus y equals 1 plus 1 minus y. That is, the leftmost sign digit of x equals negative y is, as it should be, 1, and the remaining 39 digits are those of the complement of y equals negative x equals absolute value of x. That is, those of 1 minus y. Thus, we have been led to the familiar representation of negative numbers by complementation. So it looks like they really worked through a lot of math here to arrive back at what we were expecting. I think they're doing 2's complement here because they say 1 plus 1 minus y. So that looks like 2's complement to me. So they're either doing 1's complement or 2's complement, and I think they're doing 2's complement based on what they said there. They just had to work through all the formalism of this math to get there. The connection between the digits of x and those of negative x is now easily formulated for any x is greater than or less than equals 0. Indeed, negative x is equivalent to 2 minus x equals blah, blah, blah. This digit index I equals 1 to 39 is related to our previous digit index. Blah, blah, blah. Actually, it is best to treat I as if its domain included the additional value I equals 0. Indeed, I equals 0 then corresponds to h equals 1. That is to the sign digit. In any case, I expresses the positional value of the digit, in which it refers more simply than h does. The positional value is 2 to the negative I equals 2 to the negative h minus 1. Note that if we had positioned the binary point more generally between I and I plus 1, as discussed further above, this positional value would have been 2 to the negative h minus h minus I. We now have, as pointed out previously, I equals 1. Hence, its digits obtained by subtracting every digit of x from 1 by complementing each digit. They describe complementation. Adding 1 to the rightmost position, yeah, so 2's complement. And affecting all the carries that this may cause. Note how the leftmost digit interpreted as a sign digit gets inverted by this procedure as it should be. So yeah, they really kind of like derived 2's complement from a lot of math, I guess. A subtraction x minus y is therefore performed by the accumulator as follows. And like I said, we already know about this. We saw it on Risky Business when I worked through it. Farm x plus y prime, where y prime has a digit 0 or 1, where y has a digit 1 or 0 respectively. That is, it's the complement. And then add 1 to the rightmost position. The last operation can be performed by injecting a carry into the rightmost stage of the accumulator, which again is what I showed on the show. Since this stage can never receive a carry from any other source, there being no further positions to the right. And I'll open up Milton here so you guys can see that. So let's go back to the stream canvas. Okay, so what did I write down here in such a tiny... Oh, it was just some math. Okay, so let's go to the accumulator. So I was showing how you can use it to right here. So I showed how you have the A register and another register, B register, I called it, and you have the control line for whether you want to do add or subtract, and it goes into the carry in, which is what the paper is talking about, as well as does the inversion on the B register. So this is doing the ones complement, and this is, we're getting the twos complement by adding one using the adder itself through the carry in, right? And then these are just going to all the lines in the full adder, and it does the addition, and by that method we get a subtraction. And that's what they talked about right here. 5.8, in the light of 5.7, multiplication requires special care because here the entire modulo 2 procedure breaks down. Indeed, assume that we want to compute a product x times y, and that we had to change one of the factors, say x, by an integer multiple of 2, say by 2. Then the product x plus 2 times y obtains, and this differs from the desired xy by 2 to the y. 2 to the y, however, will not in general be an integer multiple of 2, since y is not in general an integer. We will therefore begin our discussion of the multiplication by eliminating all such difficulties and assume that both factors xy lie between 0 and 1. Or to be quite precise, 0 is less than or equal to x is less than 1, 0 is less than or equal to y is less than 1. To effect such a multiplication, we first send the multiplier x into a register AR, the arithmetic register, which is essentially just a set of 40 flip-flops. These characteristics will be discussed below. We place the multiplicand y in the selectron register, SR, and use the accumulator to form and store the partial products. We propose to multiply the entire multiplicand by the successive digits of the multiplier in a serial fashion. There are, of course, two possible ways that this can be done, and I don't know what's common these days for multiplication circuits. I remember studying the logic of one of them, though. I think it was called like Karatsuba multiplication. So the Karatsuba algorithm was the first multiplication algorithm asymptotically faster than the quadratic grade school algorithm. And apparently there's a faster generalization of that. And there's another one that's even faster for a sufficiently large n. But yeah, these were known by Charles Babbage. That's interesting. But anyway, I'm not going to go through Karatsuba multiplication, I guess, for you guys, but I don't know what is common in circuits these days in terms of what you actually use to implement a multiplication circuit. I only did an adder, and I have no idea what people are doing in terms of actual ones versus like I just did, like I say, I didn't do carry lookahead, I just did a full adder that does ripple carry, and I take it this paper is going to be talking about the equivalent simple, they're saying a serial fashion, so I take it they're doing like the grade school method of multiplication. And I don't know how those circuits look, and I certainly don't know how an actual like Karatsuba algorithm circuit would look, or one of these other ones. But I actually studied this when I was pretty young, I think, because I was very interested in different ways of like doing multiplications. You've maybe seen on my stream, sometimes when I do a multiplication, I like to do this method, which is different from what you're normally taught in school. Let's see if I can find a multiplication scribble somewhere. I know I've done this on stream. I've done multiplications on paper on stream. Yeah, right here. So this is, I don't remember what this is called. Like, I think it's Vedic multiplication or something. I liked doing math on paper rather than using a calculator a lot of the time. And like I never memorize my multiplication tables, so I'm not good at like instantly knowing what a multiplication is. But I kind of learned to do math really fast on paper to make up for it. And one trick you can do is this Vedic multiplication. I think that's what this is, where what I'm doing here is I'm taking, it looks like I'm doing 20 times 1.2. Well, that one's a bad example. I did it this way, but you could have just done 2 times 12, which is 24, and then you add back the 0 and you get 240, right? But a more general case where you don't have zeros like this, if you have two-digit numbers, what you can do is normally you go in order. So you do this multiplication, and then you do this multiplication, and you like write the carries above and stuff. And then like you go to this one and you do this multiplication and you do this multiplication. But what I do is I just write all of them down here. So like I do 2 times 1 is 2. I do 0 times 2 is 0, right? And then I say 1 times 0 is 0, so I write that here in the middle. And then I say 2 times 2 is 4, so I write that down here, again, in the middle column. And then you need to add up the carries. So you get the 24 and the 0, so it's like 240. And then this was 1.2, so I put in the decimal place, and I get the 24 for 20 times 1.2. But like I did that, I learned that in like middle school or something. And around that time, I was also, this was before I was like interested in computers or anything, but I was looking at the various tricks you can do for multiplication. And I remember I found this Karatsuba algorithm. And of course, it's not practical to actually do this for a human to do this. But I remember like thinking through the steps and like trying to do the Karatsuba algorithm in my head back in the day. So I'm familiar with it, but that's just a random memory that I thought I would share with you guys. But anyway, let's continue reading here. I kind of want to just skim over this because I'm not super interested in these details. Like we just painstakingly went through adding and carries and stuff and two's complement, and it's like, yeah, I'm not really interested in how you arrived at all this stuff. So I kind of just want to skim some of this. We propose to multiply the entire multiplicand by the successive digits of the multiplier in a serial fashion. There are a couple ways you can do that. There are a few advantages from our point of view in starting with the rightmost digit. We describe a scheme for it. The multiplication takes place in 39 steps, which correspond to the 39 non-signed digits of the multiplier. Blah, blah, blah. I'm just going to skim for a while here. This process produces the product xy as desired. Note that this xy is the exact product of x and y. Since x and y are 39-digit binaries, their exact product xy is a 78-digit binary. We disregard the sign digit throughout. However, AC will only hold 39 of these. These are clearly the left 39 digits of xy. The right 39 digits of xy are dropped from AC one by one, and in the course of the 39 steps, or to be more specific, of the 39 right shifts. We will see later that these 39, the right 39 digits of xy should and will be conserved. So presumably they stick them in another register. The left 39 digits, which remain in AC, should also be rounded off, but they're not going to discuss that. To complete the general picture of our multiplication technique, we must consider how we sense the respective digits of our multiplier. There are two schemes which come to one's mind in this connection. One is to have a gate tube associated with each flip-flop of AR in such a fashion that this gate is open if a digit is 1 and closed if it is null. We would then need a 39-stage counter to act as a switch, which would successfully stimulate these gate tubes to react. A more efficient scheme is to build into AR a shifter circuit, which enables AR to be shifted one stage to the right each time AC is shifted, and to sense the value of the digit in the rightmost flip-flop of AR. The shifter itself requires one gate tube per stage. We need in addition a counter to count out the 39 steps of the multiplication, but this can be achieved by a 6-stage binary counter. Thus the latter is more economical of tubes and has one additional virtue from our point of view, which we discuss in the next paragraph. The choice of 40 digits to a word, including the sign, did I go too far up? No, that should be the continuation. But situations might arise when we desire high precision, words of greater length. A trivial illustration of this would be the computation of pi to more places than are known, which at the time was only 700 decimals. So we know quite a lot more since then. So like I say, this was what, the 40s or something that this paper was written in? So like how many digits of pi do we know today? How many digits of pi have been computed? In 2011, it was 10 trillion. So we've gone from 700 in the 40s to 10 trillion today. So that is definitely changed. And I'd say that's directly thanks to Moore's law that we've been able to compute digits of pi like that. More important instances are the solutions of n linear equations in n variables for large values of n. The extra precision becomes probably necessary when n exceeds a limit somewhere between 20 and 40. A justification of this estimate has to be based on a detailed theory of numerical matrix inversion, which will be given in a subsequent report. It is therefore desirable to be able to handle numbers of 39,000 digits and signs by means of program instructions. One way to achieve this end is to use k words to represent a 39k digit number with signs. Oh, so I think they meant not 39,000, 39k, where k is a value, maybe? I'm not totally following, but I don't really care. To represent a 39k digit number with signs, in this way, 39 digits in each 40-digit word are used, but all signed digits, excepting the first one, are apparently wasted. However, the treatment of double precision numbers in Chapter 9, it is, of course, necessary in this case to instruct the machine to perform the elementary operations of arithmetic in a manner that conforms with the interpretation of k-word complexes as single numbers. In order to be able to treat numbers in this manner, it is desirable to keep not 39 digits in a product, but 78. This is discussed in more detail in 6.6.3 below. To accomplish this end, conserving 78 product digits, we connect via our shifter circuit the rightmost digit of AC with the leftmost non-signed digit of AR. Thus, when in the process of multiplication a shift is ordered, the last digit of AC is transferred into the place in AR made vacant when the multiplier was shifted. So that's how they do it. To conclude our discussion of the multiplication of positive numbers, we note this. And like I say, I don't know if this is something that's done in modern circuits or not, because I haven't studied how multipliers are actually done. But anyway, to conclude our discussion of the multiplication of positive numbers, we note this. As described thus far, the multiplier forms the 78-digit product for a 39-digit multiplier and a 39-digit multiplicand. Blah, blah, blah. In addition to these, however, we assume some more stuff. Binary points immediately right to the signed digit. Same for XY. Prima facie, they may seem mere conventions, which affect only the mathematician's interpretation of the functioning of the machine and not a physical feature of the machine. Like in the situation of addition and subtraction. And indeed, if x had its binary point between digits I and I plus 1 from the left, and y between k and k plus 1, then our above method of multiplication would still give the correct result xy, provided that the position of the binary point in xy is appropriately assigned. Specifically, blah blah blah. Thus, it might seem that our actual positioning of the binary point immediately right to the signed digit is still a mere convention. It is therefore important to realize that it is not so. The choices of I and k actually correspond to very real physical engineering decisions. The reason for this is as follows. It is desirable to base the running of the machine on a sole consistent mathematical interpretation. It is therefore desirable that all arithmetical operations be performed with an identically conceived positioning of the binary point in AC. Applying this principle to x and y gives I equals k, hence the positions of the binary point for xy is given by blah blah blah. If this is to be the same as for x and y, then blah 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 ensues. That is, our above positioning of the binary point immediately right to the signed digit. There is one possible escape, to place into AC not the left 39 digits of xy, not counting the signed digit 0, but the digits I to I plus 38 from the left. Indeed, in this way, the position of the binary point of xy will be blah blah blah, the same as for x and y. So they were really quite focused on the importance of doing decimal calculations, but they were still in the era of doing fixed points instead of floating points. Although floating point was kind of being conceived at the time since it was mentioned in this paper. Man, how long have we been reading? So, Wow, we are already like a couple hours in. This is going to be a really long episode, but I want to do it all in one. I want to do this all in one big episode because uh, it's just further reading, and some people might want to skip it because it's not part of the book, right? But I want to read it because I'm interested, and I figured I'd want to read it on the stream, so that is what we're doing right now. So we're going to power through the rest of it here. Uh, if we wanted to use such a procedure with those drop digits really existing, then we would have to make physical arrangements for their conservation elsewhere. Also, the general mathematical planning for the machine would be definitely complicated due to the physical fact that AC now holds a rather arbitrarily picked middle stretch of 39 digits from among the 78 digits of XY. Alternatively, we might fail to make such arrangements, but this would necessitate to see to it in the mathematical planning of each problem that all products turn out to be 2 to the I minus 1 times smaller than their a priori maxima. Such an observance is not at all impossible. Indeed, similar things are unavoidable for the other operations. For example, with a factor of 2, in addition of positives or subtraction of opposite sign quantities. However, it involves a lot of significant digits, and the choice I equals 1 makes it unnecessary in multiplication. We will therefore make our choice I equals 1, that is, the positioning of the binary point immediately right of the sign digit, binding for all that follows. 5.10. We now pass to the case where the multiplier x and the multiplicand y must have either sign plus or positive or negative. That is, any combination of these signs. It would not do simply to extend the method of 5.8 to include the sign digits of x and y also. Indeed, we assume some stuff, and the multiplication procedure in question is definitely based on the greater than or equal to 0 interpretations of x and y. Hence, if x is less than 0, then it is really using x plus 2, and if y is less than 0, then it is really using y plus 2. Hence, for that stuff, it forms this stuff. Or since things may be taken modulo 2, blah blah blah, blah blah blah, it would be needed for blah blah blah. This would be a possible procedure, but there is one difficulty. As xy is formed, the 39 digits of the multiplier x are gradually lost from AR, to be replaced by the right 39 digits of xy. Unless we are willing to build an additional 40-stage register to hold x, therefore, x will not be available at the end of the multiplication. Hence, we cannot use it in the correction 2x of xy, which becomes necessary for y is less than 0. Thus, the case x is less than 0 can be handled along the above lines, but not the case y is less than 0. It is nevertheless possible to develop an adequate procedure, and we now proceed to do this. Throughout this procedure, we will maintain the assumptions blah blah blah. We proceed in several successive steps. So, I think I'm going to skip over all this stuff because I don't care about this. Like, we're reading this for the historical perspective. We're not reading it for really old school implementation details, right? We don't care about the math they were doing to arrive at these ideas. At least I don't. If you do, you can read the paper and study those things. But I'm more just interested in seeing the high level concepts this paper introduced and the kind of historical interesting details of it. So they're working through some math here. Still working through some math. Still working through some math. Looks like this is the last part of it. Doing some stuff with carries. At the present time, the development of a static accumulator is being concluded. From preliminary tests, it seems that it will add 2 numbers in about 5 microseconds, and will shift right or left in about 1 microsecond. We return now to the multiplication operation. So they had a little digression there, apparently, and now we're going back to multiplication. Okay, 5.12. It is desirable at this point in the discussion to consider rules for rounding off to n digits. In order to assess the characteristics of alternative possibilities for such properly, and in particular for the role of the concept of unbiasedness, it is necessary to visualize the conditions under which rounding off is needed. Every number x that appears in the computing machine is an approximation of another number x prime, which would have appeared if the calculation had been performed absolutely rigorously. The approximations to which we refer here are not those that are caused by the explicitly introduced approximations of the numerical mathematical setup, that is, the placement of a continuous or in example, the replacement of a continuous differential equation by a discrete difference equation. The effect of such approximations should be evaluated mathematically by the person who plans the problem for the machine, and should not be a direct concern of the machine. Indeed, it has to be handled by a mathematician, and cannot be handled by the machine, since its nature, complexity, and difficulty may be of any kind, depending upon the problem under consideration. The approximations which concern us here are these: even the elementary operations of arithmetic, to which the mathematical approximation formulation for the machines has to reduce the true, possibly transcendental problem, are not rigorously executed by the machine. The machine deals with numbers of n digits, where n, no matter how large, has to be a fixed quantity. We assume for a machine 40 digits, including the sign, so n is 39. Now the sum and difference of two n-digit numbers are again n-digit numbers, but their product and quotient in general are not. They have in general 2 to the n or infinite digits respectively. Consequently, multiplication and division must unavoidably be replaced by the machine by 2 different operations which must produce n digits under all conditions, and which, subject to this limitation, should lie as close as possible to the result of the true multiplication and division. One might call them pseudo-multiplication and pseudo-division. However, the accepted nomenclature terms them as multiplication and division with round-off. We are now creating the impression that addition and subtraction are entirely free of such shortcomings. This is only true inasmuch as they do not create new digits to the right, as multiplication and division do. However, they can create new digits to the left, that is, cause the numbers to grow out of range. This complication, which is of course well known, is normally met by the planner by mathematical arrangements and estimates to keep the numbers within range. Since we propose to have our machine deal with numbers between -1 and 1, multiplication can never cause them to grow out of range. Division, of course, might cause this complication too. The planner must therefore see to it that in every division, the absolute value of the divisor exceeds that of the dividend. Thus, the round-off is intended to produce satisfactory n-digit approximations for the product xy and the quotient x over y of two n-digit numbers. Two things are wanted of the round-off. The approximation should be good, that is, its variance from the true xy or x over y should be as small as practicable. The approximation should be unbiased, that is, its mean should be equal to the true x times y or x over y. These desired data must, however, be considered in conjunction with some further comments. Specifically, x and y themselves are likely to be the results of similar round-offs, directly or indirectly inherent, that it is, x and y themselves should be viewed as unbiased n-digit approximations of true x prime and y prime values. By talking of variances and means, we are introducing statistical concepts. Now the approximations which we are here considering are not really of statistical nature, but are due to the peculiarities, from our point of view, inadequacies of arithmetic and of digital representation, and are therefore actually rigorously and uniquely determined. It seems, however, in the present state of mathematical science, rather hopeless to try and deal with these matters rigorously. Furthermore, a certain statistical approach, while not truly justified, has always given adequate practical results. This consists of treating those digits which one does not wish to use individually in subsequent calculations as random variables with equal probable digital values, and of treating any two such digits as statistically independent, unless this is patently false. These things being understood, we can now undertake to discuss round-off procedures, realizing that we will have to apply them to the multiplication and to the division. So here we're going to go through round-off. So before we discuss how to round them off, we must know whether the true x times y and x over y are themselves unbiased approximations. So I know in like floating point, we have a variety of rounding modes that you can set. And I'm a little curious how they choose to go about rounding here. But considering that I just kind of want to skim over some of this, I don't know if we're going to really be able to tell. The round-off procedures which we can use in this connection fall into two broad classes. The first class is characterized by its ignoring all digits beyond the nth, and even the nth digit itself, which it replaces by a 1. The second class is characterized by the procedure of adding 1 unit to the n plus 1 or n plus first digit, performing the carries which this may induce, and then keeping only the n first digits. When applied to a number, blah, 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 it should be noted that the bias in the case of multiplication can be removed in various ways. However, for the reasons set forth above, we shall not complicate the machine by introducing such corrections. So they have two standard round-off methods, both unbiased to the extent to which we need this, and with the variances blah blah blah. The first one requires no carry facilities. The second one requires them. Inasmuch as we propose to form the product x prime times y prime in the accumulator, which has carry facilities, there is no reason why we should not adopt the rounding scheme described above, which has the smaller dispersion. That is, the one which may induce carries. In the case, however, of division, we wish to avoid schemes leading to carries, which we expect to form the quotient in the arithmetic register, which does not permit of carry operations. The scheme which we accordingly adopt is the one in which this is replaced by 1. This method has the decided advantage that it enables us to write down the approximate quotient as soon as we know its first n-1 digits. It will be seen in these sections below that our procedure for forming the quotient of two numbers will always lead to a result that is correctly rounded in accordance with the decisions just made. We do not consider as serious the fact that our rounding scheme in the case of division has a dispersion twice as large as that in multiplication, since division is a far less frequent operation. A final remark should be made in connection with the possible occasional need of carrying more than n equals 39 digits. Our logic control is sufficiently flexible to permit treating words as one number and thus affecting n equals 39k. In this case, the round off has to be handled differently. The multiplier produces all 78 digits of the basic 39 by 39 digit multiplication. The first 39 in the AC, the last 39 in the AR. There must then be manipulated in an appropriate manner. The divider works for 39 digits only. It seems most convenient to use this result as the first step of a series of successive approximations. Blah, blah, blah. We might mention at this time a complication which arises when a floating binary point is introduced into the machine. The operation of addition, which usually takes at most 1/10 of a multiplication, becomes much longer in a machine with floating binary, since one must perform shifts and round-offs as well as additions. It would seem reasonable in this case to place the time of an addition as about 1/3 to 1/2 of a multiplication. At this rate, it is clear that the number of additions in a problem is as important a factor in the total solution time as are the number of multiplications. We conclude our discussions of the arithmetic unit with a description of our method for handling the division operation. To perform a division, we wish to store the dividend in SR, the partial remainder in AC, and the partial quotient in AR. Before proceeding further, let us consider the so-called restoring and non-restoring methods of division. In order to be able to make a certain comparisons, we will do this for a general base m equals 2, 3, and so on. Assume for the moment that the divisor and dividend are both positive. The ordinary process of division consists of subtracting from the partial remainder at the very beginning of the process. This is, of course, the dividend. The divisor repeating this until the former becomes smaller than the latter. For any fixed positional value in the quotient in a well-conducted division, this needs to be done at most m-1 times. If after precisely k equals blah 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 repetitions of this step, the partial remainder has indeed become less than the divisor, then the digit k is put in the quotient at the position under consideration. The partial remainder is shifted one place to the left, and the whole process is repeated. Note that the above comparisons of sizes is needed at blah blah blah. Is it all reached in a well-conducted division? Then it may be taken for granted without any test, and that the partial remainder has become smaller than the divisor, and the operations on the position under consideration can therefore be concluded. In the binary system, m equals 2, there is thus only one step and only one comparison of sizes before this step. In this way, this scheme, known as the restoring scheme, requires a maximum of m minus 1 comparisons of and utilizes the digits 0, 1 to m minus 1 in each place in the quotient. The difficulty of this scheme for machine purposes is that usually the only economical method for comparing two numbers as to size is to subtract one from the other. If the partial remainder were less than the dividend, one would then have to add back into this in order to restore the remainder. Thus, at every stage, an unnecessary operation would be performed. A more symmetrical scheme is obtained by not restoring. In this method, from here on, we need not assume the positivity of divisor and dividend. One compares the sign of Rn and D. If they are of the same sign, the dividend is repeatedly subtracted from the remainder until the sign becomes opposite. If they are opposite, the dividend is repeatedly added to the remainder until the signs again become like. In this scheme, the digits that may occur in a given place in the quotient are evidently blah blah blah. The positive digits correspond to subtractions and the negative ones to additions of the dividend of the remainder. Thus, we have 2 times m minus 1 digits instead of the usual m digits. In the decimal system, that would mean 18 digits instead of 10. This is a redundant notion. The standard form of the quotient must therefore be restored by subtracting from the aggregate of its positive digits the aggregate of its negative digits. This requires carry facilities in the place where the quotient is stored. We propose to store the quotient in AR, which has no carry facilities. Hence, we could not use this scheme if we were to operate in the decimal system. The same objection applies to any base m for which the digital representation in question is redundant. That is, when this is greater than that, now this greater than that, whenever blah, 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 blah. Hence, with the use of a register, which we have so far contemplated, this division scheme is certainly exchanged from the start unless the binary system is used, or excluded from the start unless the binary system is used. Let us now investigate the situation of the binary system. We inquire if it is possible to obtain a quasi-quotient by using the non-restoring scheme and by using the digits 0 or 1 and 0 instead of 1 and negative 1. Or rather, we have to ask this question: does this quasi-quotient bear a simple relationship to the true quotient? Let us momentarily assume this question can be answered affirmatively and describe the division procedure. We start the divisor initially in AC and the dividend in SR, and wish to form the quotient in AR. We now either add or subtract the contents of SR into AC, according to whether the signs in AC and SR are opposite or the same, and insert correspondingly a 0 or 1 in the right-hand place of AR. We then shift both AC and AR, one place left, with electronic shifters that are parts of these two aggregates. At this point, we interrupt the discussion to note this: multiplication required an ability to shift right in both AC and AR. We have now found that division similarly requires an ability to shift left in both AC and AR. Hence, both organs must be able to shift both ways electronically. Since these abilities have to be present for our implicit needs of multiplication and division, it is just as well to make use of them explicitly in the form of explicit orders. It will, however, turn out to be convenient to arrange some details in the shifts when they occur explicitly under the control of those orders, differently from when they occur implicitly under the control of a multiplication or a division. For these things, the discussion of the shifts near the end 5.8 and in the third remark below on one hand, and in the third remark of 7.2 part 2 on the other hand. Let us now resume the discussion of the division. The process described above will have to be repeated as many times as the number of quotient digits that we consider appropriate to produce in this way. This is likely to be 39 or 40. We will determine the exact number further below. In this process, we form digits blah 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 when they should have been blah blah blah. Thus, we have a difference between the true quotient and the quasi-quotients, but at the same time to a one-to-one connection. It would be easy to establish the algebraical expression for this connection between z prime and z directly, but it seems better to do this as part of a discussion which clarifies all the questions connected with the process of division at the same time. We first make some general remarks. So let's skip over the general remarks. That being understood, the doubling may be performed as a simple left shift, in which the leftmost digit is allowed to be lost. Blah, blah, blah. Okay, we're still looking over general observations here. The rightmost digit is taken care of by placing a 1 into the rightmost stage of AC. At this point, an additional argument in favor of the procedure that we have adopted here becomes apparent. The procedure coincides without a need for any further corrections with the second round-off procedure that we discussed in 5.12. There remains the term -1, since this applies to the final result, and no right shifts are to follow. Carries which might go beyond the 2 to the 0 position may be disregarded. Hence, this amounts to simply changing the sign digit of the quotient x bar, replacing 0 or 1 by 1 or 0 respectively. This concludes our discussion of the division scheme. We wish, however, to re-emphasize two very distinctive features which it possesses. First, this division scheme applies equally for any combinations of signs of divisor and dividend. This is a characteristic of the non-restoring division schemes, but it is not the case for any simple known multiplication scheme. It will be remembered in particular that our multiplication procedure of 5.9 had to contain special correcting steps for the cases where either or both factors are negative. Second, this division scheme is practicable in the binary system only. It has no analog for any other base. This method of binary division will be illustrated on some examples in 5.15. 5.15, we give below some illustrative examples of the operations of binary arithmetic which were discussed in the preceding sections. Although it presented no difficulties or ambiguities, it seems best to begin with an example of addition. Okay, so we show off some various things here. The complement, we have the addition here, a subtraction, decimal notation, fractional form, blah, blah, blah. Oh, I see. So these are the decimal notations of the examples, right? So the examples are on the left in binary, and the decimal is on the right. I see. So I guess I'm not super interested in this now. It would have been nice to know they put this before reading through all the stuff before, because like I was wondering, is this 2's complement? And I guess I could have just seen that by looking here. And like we can see the addition being done here. Here's some multiplications, a division, and again, I'm not going to study these tables since we've been reading for like, I don't know, 3 hours now. So we had some round off in one example. The control. Alright, it has already been stated that the computer will contain an organ called the control, which can automatically execute the orders stored in the selectrons. Actually, for a reason stated in 6.3, the orders for this computer are less than half as long as a 40 binary digit number, and hence the orders are stored in the selectron memory in pairs. Let us consider the routine that the control performs in directing a computation. The control must know the location in the selectron memory of the pair of orders to be executed. It must direct the selectrons to transmit their pair of orders to the selectron register and then to itself. It must then direct the execution of the operation specified in the first of the two orders. Among these orders, we can immediately describe two major types. An order of the first type begins by causing the transfer of the number, which is stored at a specified memory location, from the selectrons to the selectron register. Next, it causes the arithmetical unit to perform some arithmetical operations on this number, usually in conjunction with another number, which is already in the arithmetical unit, and to retain the resulting number in the arithmetical unit. The second type order causes the transfer of the number, which is held in the arithmetical unit, into the selectron register, and from there to a specified memory location in the selectrons. It may also be that this later operation will permit a direct transfer from the arithmetical unit into the selectrons. An additional type of order consists of the transfer orders of 3.5. Further orders control the inputs and the outputs of the machine. The process described at the beginning of this paragraph must then be repeated with the second order of the order pair. This entire routine is repeated until the end of the problem. 6.2. It is clear from what we have just stated that the control must have a means of switching to a specified location in the selectron memory for withdrawing both numbers from the computation and pairs of orders. Since the selectron memory, as tentatively planned, will hold 2 to the 12 equals 4096 40-digit words. A word is either a number or a pair of orders. A 12-digit binary number suffices to identify a memory location. Hence, a switching mechanism is required which will, on receiving a 12-digit binary number, select the corresponding memory location. The type of circuit we propose to use for this purpose is known as a decoding or many-one function table. It has been developed in various forms independently by Rashman in 1943 and Crawford in 19 unknown. It consists of n flip-flops which register an n-digit binary number. It also has a maximum of 2 to the n output wires. The flip-flops activate a matrix in which the interconnections between input and output wires are made in such a way that one and only one of 2 to the n output wires is selected. That is, has a positive voltage applied to it. These interconnections may be established by means of resistors or by means of nonlinear elements such as diodes or rectifiers. All these various methods are under investigation. So what they're talking about here is a demuxer, the opposite of a multiplexer. A multiplexer is like a one-to-many, right? Or is a multiplexer many-to-one? Like a multiplexer selects from, like, you give it an input and it selects which thing to do. Whereas a demuxer is the opposite of that. But that's a concept like that is what they're talking about here. So where were we? The Selectron is so designed that 4 such function table switches are required, each with a 3-digit entry and 8 outputs. 4 sets of 8 wires each are brought out of the Selectron for switching purposes, and a particular location is selected by making one wire positive with respect to the remainder. Since all 40 Selectrons are switched in parallel, these 4 sets of wires may be connected directly to the 4 function table outputs. 6.3. Since most computer operations involve at least one number located in the Selectron memory, it is reasonable to adopt a code in which 12 binary digits of every order are assigned to the specification of a Selectron location. In those orders which do not require a number to be taken out of or into the Selectron, these digit positions will not be used. Although it has not been definitely decided how many operations will be built into the computer, that is, how many different orders the control must be able to understand, it will be seen presently that there will probably be more than 2 to the 5th, but certainly less than 2 to the 6th. For this reason, it is feasible to assign 6 binary digits for the order code. It thus turns out that each order must contain 18 binary digits, the first 12 identifying a memory location, and the remaining 6 specifying an operation. It can now be explained why orders are stored in the memory in pairs. Since the same memory organ is to be used in this computer for both orders and numbers, it is sufficient to make the length of each about equivalent. Both numbers of 18 binary digits would not be sufficiently accurate for problems which this machine will solve. Rather, an accuracy of at least 10 to the negative 10 or 2 to the negative 33 is required. Hence, it is preferable to make the numbers long enough to accommodate 2 orders. As we pointed out in 2.3 and used in 4.2 and 5.7, our numbers will actually have 40 binary digits each. This allows 20 binary digits for each order. The 12 digits that specify a memory location, and 8 more digits specifying the nature of the operation, instead of the minimum of 6 required above. It is convenient, as will be seen in further chapters, to group these binary digits into tetrads, groups of 4 binary digits. So that's the tetrad term that they were using. I'm used to the term nibble to refer to 4 binary digits. But apparently back in the day, they used the term tetrads. I like the sound of that term, though. Nibble is quite a tongue-in-cheek kind of term, whereas tetrad sounds very technical. So, hence a whole word consists of 10 tetrads, a half word or order of 5 tetrads, and of these 3 specify a memory location, and the remaining 2 specify the nature of the operation. Once the machine outside the machine, each tetrad can be expressed by a base 16 digit. The base 16 digits are best designated by symbols of the 10 decimal digits 0 to 9 and 6 additional symbols. So here they introduce the concept of hexadecimal. They suggest the letters A to F. So I wonder if this was already being done before this paper, or if this is like the first introduction of using hex. These 16 characters should appear in the typing for and the printing from the machine. The specification of the nature of the operations that is involved in an order occurs in binary form, so that another many-one or decoding function is required to decode the order. This function table will have 6 input flip-flops. The 2 remaining digits of the order are not needed. Since there will not be 64 different orders, not all 64 outputs need to be provided. However, it is perhaps worthwhile to connect the outputs corresponding to unused order possibilities to a checking circuit, which will give an indication whether a code word unintelligible to the control is received in the input flip-flops. The function table just described energizes a different output wire for each different code operation. As will be shown later, many of the steps involved in executing different orders overlap. For example, addition, multiplication, division, and going from the selectrons to the registers all include transferring a number from the selectrons to the selectron register. For this reason, it is perhaps desirable to have an additional set of control wires, each of which is activated by any particular combination of different code digits. These may be obtained by taking the output wires of the many-one function table and using them to operate tubes, which will in turn operate a one-to-many or coding function table. Such a function table consists of a matrix as before, but in this case, only one of the input wires are activated. This particular table may be referred to as the recoding function table. So this is the demuxer, and what we were talking about before is the muxer, because like a muxer, you're taking multiple input lines and you're sending a single output line. Whereas with a demuxer, you're doing the opposite of that, and that's what they're describing here. So that's the correspondence of multiplexers and demultiplexers to the one-to-many and many-to-one terminology. The 12 flip-flops operating the 4 function tables used in selecting a selectron position, and the 6 flip-flops operating the function table used for decoding the order, are referred to as the function table register, or FR. 6.4. Let us consider next the process of transferring a pair of orders from the selectrons to the control. These orders first go into SR. The order which is to be used next may be transferred directly into FR. The second order of the pair must be removed from SR, since SRI may be used when the first order is executed, but cannot as yet be placed into FR. Hence, a temporary storage is provided for it. The storage means is called the control register, CR, and consists of 20 or possibly 18 flip-flops, capable of receiving a number from SR and transmitting a number to FR. As already stated, the control must know the location of the pair of orders it is to get from the selectron memory. Normally, this location will be the one following the location of the 2 orders just executed. That is, until it receives an order to do otherwise, the control will take its orders from the selectrons in sequence. Hence, the order location may be remembered in a 12-stage binary counter, one of capable of counting 2 to the 12. To which 1 unit is added whenever a pair of orders is executed. This counter is called the control counter. The details of the process of obtaining a pair of orders from the selectron are thus as follows. The contents of CC are copied into FR. The proper selectron location is selected, and the contents of the selectrons are transferred to SR. FR is then cleared, and the contents of SR are transferred to it and CR. CC is advanced by 1 unit, so the control will be prepared to select the next pair of orders from the memory. There is, however, an exception from this last rule for the so-called transfer orders. This may feed CC in a different manner. First, the order in FR is executed, and then the order of CR is transferred to FR and executed. It should be noted that all these operations are directed by the control itself, not only the operations specified in the control word sent to FR, but also the automatic operations required to get the correct orders there. So really, they're talking about the program counter. When they say the CC, I take I take it to mean, because we're talking about these pairs of orders that they're using, right? And that's the instructions of the program. And the CC is advancing one at a time as it goes through these instructions and then executes the order. So the CC is the program counter, from what I understand, in this machine. But apparently they didn't use that terminology at the time. Since the method by means of which the control takes order pairs in sequence from the memory has been described, it only remains to consider how the control shifts itself from one sequence of control orders to another in accordance with the operations described in 3.5. The execution of these operations is relatively simple. An order calling for one of these operations contains the 12-digit specification of the position to which the control is to be switched, and these digits will appear in the left-hand 12 flip-flops of FR. All that it is required to shift the control is to transfer the contents of these flip-flops to CC. When the control goes to the selectrons for the next pair of orders, it will then go to the location specified by the number so transferred. In the case of the unconditional transfer, the transfer is made automatically. In the case of the conditional transfer, it is made only if the sign counter of the accumulator registers 0. In this report, we will discuss only the general method by means of which the control will execute specific orders, leaving the details until later. It has already been explained that when a circuit is to be designed to accomplish a particular elementary operation, such as addition, a choice must be made between a static type and a dynamic type circuit. When the design of the control is considered, this same choice arises. The function of the control is to direct a sequence of operations which takes place in the various circuits of the computer, including the circuits of the control itself. Consider what is involved in directing an operation. The control must signal for the operation to begin. It must apply whatever signals are required to specify that particular operation, and it must in some way know when the operation has been completed so that it may start the succeeding operation. Hence, the control circuits must be capable of timing the operations. It should be noted that timing is required whether the circuit performing the operation is static or dynamic. In the case of a static type circuit, the control must apply static control signals for a period of time sufficient to allow the output voltages to reach the steady state condition. In the case of a dynamic type circuit, the control must send various pulses at proper intervals to the circuit. If all circuits of a computer are static in character, the control timing circuits may likewise be static, and no pulses are needed in the system. However, though some of the circuits of the computer we are planning will be static, they will probably not all be. So, and hence pulses as well as static signals must be supplied by the control to the rest of the computer. There are many advantages in deriving these pulses from a central source called the clock. The timing may then be done either by means of counters, counting clock pulses, or by means of electrical delay lines. An RC circuit is here regarded as a simple delay line. Since the timing of the entire computer is governed by a single pulse source, the computer circuits will be said to operate as a synchronized system. And so, this is something that we've really kind of seen in detail with RISC-V and the Hi-5 We've really kind of dove into and learned about the various clock sources that it has. The clock plays an important role both in detecting and in localizing the errors made by the computer. One method of checking which is under consideration is that of having two identical computers which operate in parallel and automatically compare each other's results. Both machines would be controlled by the same clock, so they would operate in absolute synchronism. It is not necessary to compare every flip-flop of one machine with the corresponding flip-flop of the other. Since all numbers and control words pass through either the selectron register or the accumulator soon before or soon after they are used, it suffices to check the flip-flops of the selectron register and the flip-flops of the accumulator, which hold the number register there. In fact, it seems possible to check the accumulator only. The checking circuit would stop the clock whenever a difference appeared, or stop the machine in a more direct manner if an asynchronous system is used. Every flip-flop of each computer will be located at a convenient place. In fact, all neons will be located on one panel, the corresponding neons of the two machines being placed in parallel rows so that one can tell at a glance, after the machine has been stopped, where the discrepancies are. So that's definitely an interesting design. That's certainly archaic, I think. The merits of any checking system must be weighed against its cost. Building two machines may appear to be expensive, but since most of the cost of a scientific computer lies in development rather than production, this consideration is not so important as it might seem. Experience may show that for most problems, the two machines need not be operated in parallel. Indeed, in most cases, purely mathematical external checks are possible. Smoothness of the results, behavior of differences of various types, validity of suitable identities, redundant calculations, etc. All of these methods are usually adequate to disclose the presence or absence of error in toto. Their drawback is only that they may not allow the detailed diagnosing and locating of errors at all or with ease. When a problem is run for the first time, so that it requires special care, or when an error is known to be present and has to be located, only then will it be necessary, as a rule, to use both machines in parallel. Thus, they can be used as separate machines most of the time. The essential features of such a method of checking lies in the fact that it checks the computation at every point, and hence detects transient errors as well as steady-state ones, and stops the machine when the error occurs so that the process of localizing the fault is greatly simplified. These advantages are only partially gained by duplicating the arithmetic part of the computer, or by following one operation with a complement operation, multiplication by division, etc. Since this fails to check either the memory or the control, which is the most complicated though not the largest part of the machine. The method of localizing errors, either with or without a duplicate machine, needs further discussion. It is planned to design all the circuits, including those of the control of the computer, so that if the clock is stopped between pulses, the computer will retain all its information in flip-flops so that the computation may proceed unaltered when the clock is started again. This principle has already demonstrated its usefulness in the ENIAC. This makes it possible for the machine to compute with the clock operating at any speed below a certain maximum, as long as the clock gives out pulses of constant shape regardless of the spacing between pulses. In particular, the spacing between pulses may be made indefinitely large. The clock will be provided with a mode of operation in which it will emit a single pulse whenever instructed to do so by the operator. So, like stepping in a debugger. By means of this, the operator can cause the machine to go through an operation step by step, checking the results by means of the indicating lamps connected to the flip-flops. It will be noted that this design principle does not exclude the use of delay lines to obtain delays, as long as these are only used to time the constituent operations of a single step, and have no part in determining the machine's operating repetition rate. Timing coincides by means of delay lines is excluded, since this requires a constant pulse rate. Or timing coincidences by means of a delay line is excluded, since this requires a constant pulse rate. 6.6. The orders which the control understands may be divided into two groups. Those that specify operations which are performed within the computer, and those that specify operations involved in getting data into and out of the computer. At the present time, the internal operations are more completely planned than the input and output operations, and hence they will be discussed more in detail than the latter, which are treated briefly in 6.8. The internal operations which have been tentatively adopted are listed in Table 1. It has already been pointed out that not all of these operations are logically basic, but that many can be programmed by means of others. In the case of some of these operations, the reasons for building them into the control have already been given. In this section, we will give reasons for building the other operations into the control, and we will explain in the case of each operation what the control must do in order to execute it. In order to have a precise mathematical meaning of the symbols which are introduced in what follows clearly in mind, the reader should consult the table at the end of the report for each new symbol, in addition to the explanations given in the text. We're not going to bother doing that. Throughout what follows, S of x will denote the memory location number x in the selectron. Accordingly, the x which appears in S of x is a 12-digit binary in the sense of 6.2. The 8 addition operations, blah, 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 involves the following possible 4 steps. First, clear SR and transfer into the number at SX. Second, clear AC if the order contains the symbol C. Do not clear AC if the order contains the symbol H. Third, add the number in SR, or its negative. That is, in our present system, its complement will, with respect to the 1, and to AC. If the order does not contain the symbol M, use the number in SR, or its negative, according to whether the operation contains the symbol plus or minus. If the order contains the symbol M, use the number in SR, or its negative, according to whether the sign of the number in SR and the symbol, positive or negative, in the order do or do not agree. Fourth, perform a complete carry. Building the last 4 addition operations, those containing the symbol M, and to the control is fairly simple. It calls only for one extra comparison of the sign in SR and the plus or minus in the order, the third step above. And it requires, therefore, only a few tubes more than required for the first 4 addition operations, those not containing the symbol M. These facts would seem of themselves to justify adding the operations in question, plus and minus the absolute value, but it should be noted that these operations can be programmed out of the other operations of Table 1 with correspondingly few orders, 3 for absolute value and 5 for minus absolute value, so that some further justification for building them in is required. The absolute value order is frequently in connection with the orders L and R, while the minus absolute value order makes the detection of a 0 very simple by merely detecting the sign of the negative absolute value of n. If negative absolute value of n is greater than or equal to 0, then n equals 0. The operation of S of x to R involves the following 2 steps. First, clear SR and transfer SX to it. Second, clear AR and add the number in the selectron register into it. The operation of R to AC merits more detailed discussion. Since there are alternative ways of removing numbers from AR, such numbers could be taken directly to the selectrons as well as into AC, and they could be transferred to AC in parallel, in sequence or in sequence parallel. It should be recalled that while most of the numbers that go into AR have come from the selectrons and thus need not be returned to them, the result of a division and the right-hand 39 digits of a product appear in AR. Hence, while an operation for withdrawing a number from AR is required, it is relatively infrequent and therefore it need not be particularly fast. We are therefore considering the possibility of transferring, at least partially in sequence, and of using the shifting properties of AC and of AR for this. Transferring the number to the selectron via the accumulator is also desirable if the dual machine method of checking is employed, for it means that even if numbers are only checked in their transit through the accumulator, nevertheless, every number going into the selectron is checked before being placed there. The operation Sx times R to AC involves the following 6 steps. We clear the SR and transfer Sx, the multiplicand, into it. Second, 39 steps, each of which consist of the 2 following parts. Add, or rather shift, the sign digit of SR into the partial product in AC, or add all but the sign digit of SR into the partial product of AC, depending upon whether the rightmost digit in AR is 0 or 1, and effect the appropriate carries. Then shift AC and AR to the right, fill the sign digit of AC with the 0, and the digit of AR immediately right of the sign digit, positional value to the negative 1, with the previously rightmost digit of AC. There are ways to save time by merging these two operations with the rightmost digit in AR when the rightmost digit in AR is 0, but we will not discuss them here more fully. Third, if the sign digit in SR is 1, that is negative, then inject a carry into the rightmost stage of AC and place a 1 in the sign digit of AC. Fourth, if the original sign digit of AR is 1, that is negative, then subtract the contents of SR from AC. Fifth, if a partial carry system was employed in the main process, then a complete carry is necessary at the end. Sixth, the appropriate round-off must be effected. It will be noted that since any number held in AC at the beginning of the process is gradually shifted into AR, it is impossible to accumulate sums of products in AC without storing the various products temporarily in the selectrons. While this is undoubtedly a disadvantage, it cannot be eliminated without constructing an extra register, and this does not at the moment seem worthwhile. On the other hand, saving the right-hand 39 digits of the answer is accomplished with very little extra equipment, since it means connecting 2 to the negative 39 stage of AC to the 2 to the negative 1 stage of AR during the shift operation. The advantage of saving these digits is that it simplifies the handling of numbers of any number of digits in the computer. Any number of 39k binary digits where k is an integer and sign can be divided into k parts, each part being placed in a separate selectron position. Addition and subtraction of such numbers may be programmed out of a series of additions or subtractions of the 39-digit pairs, the carryover being programmed by means of CC to S of x and CC prime to S of x operations. If the 2 to the 0 stage of AC registers negative after the addition of two 39-digit pairs, a carryover has taken place, and hence 2 to the negative 39 must be added to the sum of the next parts. A similar procedure may be followed in multiplication if all 78 digits of the product of the two 39-digit pairs are kept, as is planned. Since it would greatly complicate the computer to make provisions for holding and using a 78-digit dividend, it is planned to program 39k digit division in one of the ways described at the end of 5.12. Okay, on to division. The operation of division, AC divided by S of x over R, involves the following 4 steps. Clear SR and transfer Sx, the divisor, into it. Clear AR. 39 steps, each of which consists of the following 3 parts. Since the signs of the contents of AC, the partial remainder, and of SR, and sense whether they agree or not. Shift AC and AR left. In this process, the previous sign digit of AC is lost. Fill the rightmost digit of AC, after the shift with a 0, and the rightmost digit of AR before the shift with 0 or 1, depending on whether there was a disagreement or agreement in A. Add or subtract the contents of SR into AC, depending on the same alternative as above. Fourth, fill the rightmost digit of AR with a 1 and change its sign digit. For the purpose of timing the 39 steps involved in division, a 6-stage counter, capable of counting to 2 to the 6 equals 64, will be built into the control. This same counter will also be used for timing the 39 steps of multiplication, and possibly for controlling AC when a number is being transferred between it and a tape in either direction. Alright, 6.6.5. The 3 substitution operations involve transferring all or part of the numbers held into AC into the selectrons. This will be done by means of a gate tubes connected to the registered flip-flops of AC. 40 such tubes are needed for the total substitutions. The partial substitution and this require that the left-hand 12 digits of the number held in AC be substituted in the proper places in the left-hand and right-hand orders, respectively. This may be done by means of extra gate tubes or by shifting the number in AC and using the gate tubes required for this. This scheme needs some additional elaboration. When the order directing and the order suffering the substitution are the 2 successive halves of the same word. That is, when the latter is already in FR at the time when the former becomes operative in CR, so that the substitution effected on the selectrons comes too late to alter the order which has already reached CR, to become operative at the next step in FR. There are various ways to take care of this complication, either by some additional equipment or by appropriate prescriptions in coding. We will not discuss them here in more detail, since the decisions in this respect are still open. The importance of the partial substitution operations can hardly be overestimated. It has already been pointed out that they allow the computer to perform operations it could not otherwise conveniently perform, such as making use of a function table stored in the selectron memory. Furthermore, these operations remove a very sizable burden from the person coding problems, for they make possible the coding of classes of problems in contrast to coding each individual problem separately. Any program sequence may be stated in general form, that is, without selectron location designations for the numbers being operated on, and the selectron locations of the numbers to be operated on substituted whenever that sequence is used. As an example, consider a general code for nth order integration of m total differential equations for p steps of independent variable t, formulated in advance. Whenever a problem requiring this rule is coded for the computer, the general integration sequence can be inserted into the statement of the problem, along with coded instructions for telling the sequence where it will be located in the memory. Whenever this sequence is to be used by the computer, it will automatically substitute the correct values of m and p and delta t, as well as the locations of the boundary conditions and the descriptions of the differential equations into the general sequence. A library of such general sequences will be built up, and facilities provided for convenient insertion of any of these into the coded statements of a problem. When such a scheme is used, only the distinctive features of a problem need to be coded. So really, what we're talking about is functions, right? I mean, this is like talking about building up a library of sequences. What we're talking about here is that we can have procedures. That's kind of, I think, the advancement that they made here, due to their control flow abilities that they decided on. So anyway, let's keep reading here. The manner in which the control-shift operations are realized has been discussed and needs no further comment. One basic question which must be decided before a computer is built is whether the machine is to have a so-called floating binary or decimal point. While a floating binary point is undoubtedly very convenient in coding problems, building it into the computer adds greatly to its complexity, and hence a choice in this matter should receive very careful attention. However, it should first be noted that the alternative ordinarily considered, building a machine with a floating point versus doing all computations with fixed point, are not exhaustive, and hence that the arguments generally advanced for the floating point are only of limited validity. Such arguments overlook the fact that the choice with respect to any particular operation, except for certain basic ones, is not between building it into the computer and not using it at all, but rather between building it into the computer and programming it out of operations built into the computer. Building a floating binary point into the computer will not only complicate the control, but will also increase the length of a number and hence increase the size of the memory and the arithmetic unit. Every number is effectively increased in size, even though the floating point is not needed in many instances. Furthermore, there is considerable redundancy in a floating binary point type of notation, for each number carries with it a scale factor, while generally speaking, a single scale factor will suffice for possibly extensive set of numbers. By means of the operations already described in the report, a floating point can be programmed. So really, I mean, it seems like they hadn't really thought of the idea of having a separate floating point unit. They were kind of thinking, we're either going to go with the integer, the ALU, and use it with fixed point, or we're going to have a floating point unit and not like in a traditional ALU. Apparently, the idea of using both in the same machine wasn't such a common idea. Maybe it just wasn't practical at this point in time. Because to me, it seems pretty obvious in this day and age, well, you have an ALU, you have an FPU, you know. But it seems that these guys decided not to go with the FPU. While additional memory capacity is needed for this, it is probably less than that required by a built-in floating point, since a different scale factor does not need to be remembered for each number. To program a FPU, or a floating point, involves detecting where the first zero occurs in the number in AC. Since AC has shifting facilities, that can best be done by means of them. In terms of the operations previously described, this would require taking the given number out of AC and performing a suitable arithmetical operation on it. For a multiple right shift multiplication, for a multiple left shift, either one division or as many doublings, that is additions, as the shift has stages. However, these operations are inconvenient and time-consuming, so we propose to introduce two operations, L and R, in order that this, the single left and right shift, can be accomplished directly. These operations make use of facilities already present in AC, and hence add very little equipment to the computer. It should be noted that in many instances, a single use of L and possibly of R will suffice in programming a floating point. But if the two factors in a multiplication have no superfluous zeros, the product will have at most one Superfluous, 0. If some stuff, blah, blah, blah. This is similarly true in division, blah, blah, blah. In addition and subtraction, any numbers growing out of range can be treated similarly. Numbers which decrease in these cases, that is, develop a sequence of zeros at the beginning, are really mathematically losing precision. Hence, it is perfectly proper to omit formal readjustments in this event. Indeed, such a true loss of precision cannot be obviated by any formal procedure, but if at all, only by a different mathematical formulation of the problem. 6.7. Table 1 shows that many of the operations which the control is to execute have common elements. Thus, addition, subtraction, multiplication, and division all involve transferring a number from the selectrons to SR. Hence, the control may be simplified by breaking some of the operations up into more basic ones. A timing circuit will be provided for each basic operation, and one or more such circuits will be involved in the execution of an order. The exact choice of basic operations will depend on how the arithmetic unit is built. In addition to the timing circuits needed for executing the orders of Table 1, 2 such circuits are needed for the automatic operations of transferring orders from the selectron register to CR and FR, and for transferring an order from CR to FR. In normal computer operation, these 2 circuits are used alternatively, so a binary counter is needed to remember which is to be used next. In these operations, the first order of a pair is ignored, so the binary counter must be altered accordingly. The execution of a sequence of orders involves using the various... Okay, and here we see the table. Timing circuits in a sequence. When a given timing circuit has completed its operation, it emits a pulse which should go to the timing circuit to be used next. Since this depends upon the particular operation being executed, these pulses are routed according to the signal received from the decoding and recoding function tables activated by the 6 binary digits specifying an order. So let's take a look at the table here of the operations they had. So clear accumulator and add number located at position X in the selectrons into it. Clear accumulator and subtract number. Clear and add absolute value of number. Subtract absolute value. Add number located at a position. Subtract number located at position. Add absolute value of number at position. Subtract absolute value of number at position. Clear register and add number located at position X. Clear accumulator and shift a number held in register into it. Clear accumulator and multiply the number located at position X. Clear register and divide. Shift left, shift right, conditional, shift the control. So that must be like a conditional jump then, those 2. Transfer the number in the accumulator to position X. Replace the left-hand 12 digits of the left-hand order located at position X by the left-hand 12 digits in the accumulator. Here's for the right-hand order. Multiply the number of the accumulator by 2, leaving it there. Divide the number in the accumulator by 2, leaving it there. So those are the operations they had. Very interesting. In this section, we will consider what must be added to the control so that it can direct the mechanisms for getting data into and out of the computer, and also describe the mechanisms themselves. Three different kinds of input-output mechanisms are planned. First, several magnetic wire storage units operated by servo mechanisms controlled by the computer. Second, some viewing tubes for graphical portrayal of results. Third, a typewriter for feeding data directly into the computer, not to be confused with the equipment used for preparing and printing from magnetic wires. As presently planned, the later will consist of a modified teletypewriter equipment. Since there already exists a way of transferring numbers between the selectrons and AC, therefore AC may be used for transferring numbers from and to a wire. The later transfer will be done serially and will make use of the shifting facilities of AC. Using AC for this purpose eliminates the possibility of computing and reading from or writing on the wires simultaneously. However, simultaneous operation of the computer and the input-output organ requires additional temporary storage and introduces a synchronizing problem, and hence it is not being considered for the first model. Since at the beginning of the problem the computer is empty, facilities must be built into the control for reading a set of numbers from a wire when the operator presses a manual switch. As each number is read from a wire into AC, the control must transfer it to its proper location in the selectrons. The CC may be used to count off these positions in sequence, since it is capable of transmitting its contents to FR. A detection circuit on CC will stop the process when the specified number of numbers has been placed in the memory, and the control will then be shifted to the orders located in the first position of the selectron memory. It has already been stated that the entire memory facilities of the wires should be available to the computer without human intervention. This means that the control must be able to select the proper set of numbers from those going by. Hence, additional orders are required for the code. Here, as before, we are faced with two alternatives. We can make the control capable of executing an order of the form: take numbers from positions P to P plus S on wire number K and place them in the selectron locations V to V plus S. Or we can make the control capable of executing some less complicated operations, which together with the already given control orders are sufficient for programming the transfer operation of the first alternative. Since the latter scheme is simpler, we adopt it tentatively. The computer must have some way of finding a particular number on a wire. One method of arranging for this is to have each number carry with it its own location designation. A method more economical of wire memory capacity is to use the selectron memory facilities to remember the positions of each wire. For example, the computer would hold the number T1, specifying which number on the wire is in position to be read. If the control is instructed to read the number at position P1 on this wire, it will compare P1 and T1, and if they differ, cause the wire to move in the proper direction. As each number on the wire passes by, one unit is added or subtracted to T1, and the comparison repeated. When P1 equals T1, numbers will be transferred from the wire to the accumulator, and then the proper location in the memory. Then both T1 and P1 will be increased by 1, and the transfer from the wire to the accumulator to memory repeated. This will be iterated until T1 plus S and P1 plus S are reached, at which time the control will direct the wire to stop. Under this system, the control must be able to execute the following orders with regards to each wire: start the wire forward, start the wire in reverse, stop the wire, transfer from wire to AC, and transfer from AC to wire. In addition, the wire must signal the control as each digit is read and when the end of a number has been reached. Conversely, when recording is done, the control must have a means of timing the signals sent from AC to the wire and of counting off the digits. The 2 to the 6th counter used for multiplication and division may be used for the latter purpose, but the other timing circuits will be required for the former. If the method of checking by means of two computers operating simultaneously is adopted, and each machine is built so that it can operate independently of the other, then each will have a separate input-output mechanism. The process of making wires for the computer must then be duplicated, and in this way, the work of the person making a wire can be checked. Since the wire servo mechanisms cannot be synchronized by the central clock, a problem of synchronizing the two computers when the wires are being used arises. It is probably not practical to synchronize the wire feeds to within a given digit, but this is unnecessary since the numbers coming from the two organs AC need not be checked as the individual digits arrive, but only prior to being deposited in the selectron memory. Since the computer operates in the binary system, some means of decimal binary and binary to decimal conversions is highly desirable. Various alternative ways of handling this problem have been considered. In general, we recognize two broad classes of solutions to this problem. First, the conversion problems can be regarded as simple arithmetic processes and programmed as subroutines out of the orders already incorporated in the machine. The details of these programs, together with the more complete discussion, are given fully in Chapter 9, where it is shown, among other things, that the conversion of a word takes about 5 milliseconds. Thus, the conversion time is comparable to the reading or withdrawing time for a word, about 2 milliseconds, and is trivial as compared to the solution time for problems to be handled by the computer. It should be noted that the treatment proposed there presupposes only that the decimal data presented to or received from the computer are in tetrads, and each tetrad being the binary coding of a decimal digit. The information, or precision, represented by a decimal digit being actually equivalent to that represented by 3.3 binary digits. The coding of decimal digits into tetrads of binary digits and the printing of decimal digits from such tetrads can be accomplished quite simply and automatically by slightly modified teletype equipment. Second, the conversion problems can be regarded as unique problems and handled by separate conversion equipment, incorporated either in the computer proper or associated with the mechanisms for preparing and printing from magnetic wires. Such converters are really nothing other than special-purpose digital computers. They would seem to be justified only for those computers which are primarily intended for solving problems in which the computation time is small, compared to the input-output time, to which class our computer does not belong. It is possible to use various types of cathode ray tubes, and in particular selectrons for the viewing tubes, in which case programming the viewing operation is quite simple. The viewing selectrons can be switched by the same function tables that switch the memory selectrons. By means of the substitution operation, 6-digit numbers specifying the abscissa or abscissa and ordinate of the point, 6 binary digits represent a precision of 1 part in 2 to the 6 equals 64, that is, of about 1.5%, which seems reasonable in such a component, can be substituted in this order, which will specify that a particular one of the viewing selectrons is to be activated. As was mentioned above, the mechanisms used for preparing and printing from wire, for the first model at least, will be modified teletype equipment. We are quite fortunate in having secured the full cooperation of the Ordnance Development Division of the National Bureau of Standards in making these modifications and designing and building some additional equipment. By means of this modified teletype equipment, an operator first prepares a checked paper tape and then directs the equipment to transfer the information from the paper tape to the magnetic wire. Similarly, a magnetic wire can transfer its contents to a paper tape, which can be used to operate a teletypewriter. Studies are being undertaken to design equipment that will eliminate the necessity for using paper tapes. As was shown in 6.6.5, the statement of a new problem on a wire involves data unique to that problem interspersed with data found on a previously prepared on previously prepared paper tapes are magnetic wires. The equipment discussed in the previous paragraph makes it possible for the operator to combine conveniently these data onto a single magnetic wire ready for insertion into the computer. It is frequently very convenient to introduce data into a computation without producing a new wire. Hence, it is planned to build one simple typewriter as an integral part of the computer. By means of this typewriter, the operator can stop the computation, type in a memory location, which will go to the FR, type in a number, which will go to the AC, and then be placed in the first mentioned location, and start the computation again. There is one further order that the control needs to execute. There should be some means by which the computer can signal to the operator when a computation has been concluded, or when the computation has reached a previously determined point. Hence, an order is needed which will tell the computer to stop and to flash a light or to ring a bell. And that's the origin of the system bell. So that was quite the read. I've got to say, I going into this, I thought this was going to be more of a overview of the concepts of like when kind of the what's known as the von Neumann architecture. I thought it would be like a high level overview of that concept when it was like first like thought of, right? And we certainly see it throughout this document, throughout this paper. It's very clear, kind of a lot of interesting similarities to what we have today and a few peculiarities of the time. But it's a very interesting look in the history of that. But it was very specific. It was very technical and really focused on the design and implementation of a specific machine that they were working on, right? This was really a paper discussing the logical design of an electronic computing instrument. They didn't mean in an abstract sense. They meant a very specific machine, whereas I was expecting this to be about more of an abstract thing. Just the concepts of computer architecture is what I was expecting. So I was surprised to see that it was so specific, and it was quite laborious to read through a lot of the specifics, and I skipped over a lot of the mathematical specifics when I read it, as you just saw, if you managed to listen through all of that. But I wonder, is that actually the paper that I thought it was? I'm curious now. I want to see in the historical perspectives here. Were there other papers by Burks and Goldstine? I'm not totally sure if that was actually the paper I was gonna think it was, but I mean, it was a very interesting read, regardless. So a classic paper explaining computer architecture and software before the first starred program computer was built. We quote extensively from it in Chapter 3, so this is the paper I thought it was. It simultaneously explained computers to the world and was a source of controversy because the first draft did not give credit to Eckert and Mauchly. And that was the 1946 paper, preliminary discussion of the logical design of an electronic computing instrument. Yeah, that's what we just read. So yeah, that was the paper. We've been streaming for, let me see here. When did I start this episode? So it's been like 4 hours, maybe 3.5. No, closer to 4. So that was Wow. That was quite quite a marathon to read through that entire thing in a single sitting. Uh, but yeah. Anyway, that's going to end it for this episode. For those watching on the stream, I'm going to continue streaming after this and do Risky Business because this is a marathon tonight. But yeah, a lot of the time of this marathon was taken up by that. I thought it was going to be like, just read an hour of a paper that gives like a high level overview of computer architecture, not like 4 hours of reading very technical documentation of a machine that was being built in the 40s, but it was what it was. Anyway, thank you everyone who tuned in today, and thank you everyone who watches on the YouTube archive, which is available at risky.tv. You can follow me on Twitter at HMN_risky to get updates about the series. And thank you to everyone who financially supports the series on Patreon. If you would like to financially contribute to what I do, you can do so at patreon.risky.tv. I will see you in the next episode, and stay risky, everyone.